Okay, good morning, everybody. Today we are doing this last unit. I'm actually really relieved. Even today morning, I was just talking to the sir and I said, when I got up, I was feeling like really relaxed. Then I was thinking, what happened to make me relax? Because I'm done with you, English medium and also Sinhala medium up to this unit 13. So this is the last little unit. When we are talking about this unit 14, this is the little syllabus. Okay. What I want to tell you guys is unit 14 is not important. Unit 14 is important, but the importance is very, very little. Last question, 10th essay question coming from this unit, only from this unit. And usually this gets like, again, one single question. So 150 marks, 7.5 exact marks up to from your last 100. So if you get to the 100, you're going to get 7.5. That is for each and every single essay question, you're going to get 7.5. But the problem here is from this 150, reaching to 75 is extremely harder. So I advise you not to choose 10th question as full essay question that you are doing for the exam. 9th question comes with inorganic and electrochemistry, sometimes a little part of unit 5. So it may be equilibrium that you can do. So those questions, if you give the maximum proper answer, they are giving maximum marks. With those, you can reach 150, but you never can reach 150 from this unit. So don't ever go with that. But in your MCQs, usually they would give like, the 3 to 5 question or 3 to 6 question, let's say. So to reach 100 marks, you guys definitely need that. So that is why we are doing unit 14, only to fulfill that couple of MCQs. Studying or the memorizing unit 14 is easier because same way that you did inorganic chemistry, you are just reading whatever the diagram or whatever these equations you have, you are just writing. This is like a little story. The unit is industrial chemistry and environmental pollution. So the very first part, we are talking about how we use whatever the knowledge that we gain from unit 1 to unit 13, how we use them in industry. Through that, you can make this as your, up to here, from here, as your little, this summarization. So in this unit 14, you're going to talk about this extraction of magnesium, then sodium hydroxide, then soap, then sodium carbonate, then ammonia, then nitric acid, sulfuric acid, titanium, iron, then some polymers, rubber and rubber-related compounds and plastics, then vinegar, ethanol, how to extract essential oil by the steam distillation, we done that, and then the biodiesel. Okay, those are the industries that we are discussing in this unit. So you can make a little short note, not somewhere, but on this. Same way that I asked you guys to do for inorganic and equilibrium, whatever the short note you are making, you're going to do on this paper, on this photocopy, because there is a lot that you have to go through the photocopy. You cannot make everything as a as a short note. So the part you are going normal, you can go with that. Let's say you are making short note with 2-3 pages. So maybe you can just make it a box bracket, a huge box bracket like this. This part you shouldn't read because you have a little short note you have written somewhere here. Understood? Let's say you're gonna go with this page, then you feel like nothing to get from page. You can write box bracket here, and you can write your short note somewhere here. Then you don't have to read this one. You are only reading this little short note. That will make the short note to make it easier. Okay, the first part is the industrial part, and then the second part is the environmental pollution. Okay, this is the environmental pollution part. That part we are talking about I can't find this soil pollution here. I know it's here. So that part consists with water pollution, air pollution, and this part is water pollution. Sorry, air pollution, then water pollution, and then the last part is the land or this earth pollution, the soil pollution. Those three parts. Once you go to the industries, then this. So each of these topics are very, very small, like only couple of pages. Even if you read this on your own, you can understand this one. But when somebody is reading it for you, and when I'm explaining the processes little going deeper with more description, you can understand this very nicely. Come, darling. Whatever I have explained already, listen that part, okay? Listen, it's important. Okay, so we're going to start then. So what I'm doing is, I'm just going to read this note for you. Only thing I'm doing is, I'm going to read this. Dhoni, you have a little part or what? Where's the other part? Is this all? Okay, so you, a small part. No, it's okay. You can go with her. When there is something to write on the page number, you just write the page number, go through the recording, then write that. Then you don't have to waste your time twice. Anyway, listening is the most important part on this one. What I'm going to do is, I'm going to read the note, then you are just listening. Whenever you feel like part is not understanding, you can ask me questions. Or otherwise, I'm explaining when I feel like that you are not understanding those parts. Okay, so we have two different parts here to go on. Industrial chemistry, that part explained up to here, then the water, soil, and air pollution. So the first part is industrial chemistry. So I'm going to go with that. Okay, listen this from the beginning carefully, okay? Okay, industrial chemistry. Chemical industries. Colossal mean big changes, okay? Colossal changes occurred in the mode of production and the force of production during the periods identified as the first industrial revolution. Okay, this is a little introduction. As all the introduction of we came from unit 1 to unit 13, introduction is not important. You are just understanding, that's all, okay? And the second industrial revolution in modern civilization, along with the diversified market concepts, consumerism, that you are using products based on the basic requirements of human, world scale productions and services speed up making profits. World scale means to the world we are making things. Various types of technological tools and methods of productions were created for this. With industrialization, environmental and social problems tend to emerge. Yeah, during the industrialization, they made different devices which make like, let's say something is evolving, like, you know, the vehicles emitting these carbon monoxide and sulfur dioxide. So those are pollutants. Here, more attention had to be paid to reduce the risk of environmental problems and disasters. Also disasters, they are explaining it later. When you are arranging, when you are analyzing, when you are planning any industry, to avoid, you have to think of risk of environmental problems and disasters. Optimize efficiency, the product improvement, and increase productivity. How much it is improving. Alongside the gaming of special players by chemical industries, in the process of industrial production, a field of study of which came to be known as a chemical engineering emerged. So after all this, the topic of chemical engineering or the different field of chemical engineering are there now. It's a well-established discipline. Okay, so we are talking about some of the products that we are doing in this unit, and some are like we are not using. Anyway, iron, ammonia, sulfuric acid, nitric acid, caustic soda, petroleum can be given as the main chemical products in the world, especially medicines, monomers, polymers. Monomers used to make polymers, lubricants to avoid abrasion, organic dyes for coloring, Examples for the production manufactured using organic compounds obtained from the petroleum industry. Plastic and rubber goods, cosmetics, soap, detergents, adhesives, paper, glass, salt, sugar, used in day-to-day life as some more examples for the production of chemical industries. Production of salt using seawater is one of the chemical industries in our country. Production of soap using major chemical produced in the world. Production of various materials and goods using natural rubber latex. And production of cement, paint, glass are some of the chemical industries carried out in our country at present. So we are making in our country rubber latex compounds, paints, glass. Like those are general information, general knowledge. So that's why we can go with unit 14. We cannot get full marks. Okay. So they are asking little parts of this general knowledge. So that's what happened with unit 14. Chemical industries spread out and established in global scale are diverse. They can be classified as chemical industries producing organic chemicals and inorganic chemicals. In addition, they can also be classified as industries which produce agrochemicals, medicine, lubricants, dyes, metals, and other substances. There are different various methods of defining these different industries. Only few industries are discussed as examples which are based on modern knowledge and technology. Paying attention on the environment, health, and social issues at present worldwide, the industries suitable for our country are considered. Management of the knowledge on such is an entrance to industrial chemistry discussed here. Okay, that part you can forget. Here some stuff are there you're supposed to write, okay? Requirements to be considered in establishing a chemical industry. There are requirements that should be considered when establishing a chemical industry. Some of them are given below. Capital. What is the capital? Whatever the assets. Maybe it's financially, maybe some other assets which used to produce economically useful products. Okay, let's write that under in front of capitals. Assets which used to produce economically useful products. Economically useful products. Okay, supply of raw materials. What is the meaning of that? Supply of raw material mean whatever the industrial material that we use to produce our final product. So let's write there. So initial material for production. Initial material for production. Labor can be human labor, or have you guys, if you guys have been to these other countries, you guys have seen earlier, like let's say the microwave is, we are putting the food in microwave, heat it up, so we are opening the door and we're going to get food out. Now we are not doing that, so we just have to give them the command. Now they are like little robots, they have improved, so they are getting the food, so they are putting it in microwave, then they do the thingy, and they are serving it back to us. So the machine labor, it is there now. Earlier it was like unbelievable something, now it is there. So let's write human and machines. Human and machines. You guys know the technology is like something we cannot explain using, maybe years you need to explain all the technologies, like very speedily it's developing now. We can use the technology for production and also to waste management. That is a main part now. You cannot install any industry without explaining how you manage your whatever the waste products, whatever you are not using, and to prevent environmental pollution. We can use the technology. Let's write production / waste management waste management / to prevent environmental pollution. To prevent environmental pollution. For all those things, we can use technology. Okay, what is the meaning of assurance of production process? It simply means thinking big, let's say not thinking too much that you are installing some sort of a company, but later maybe you don't have enough money, or maybe you don't have human power. Maybe to get raw material, let's say that we need, let's say we need seawater. So if you are installing our company, our productions, whatever the place, we have to do it closer to the sea. So that's supposed to be come again when you are doing a production. So the raw material coming continuously, labors, let's say that, like, let's say the tea estates, if we install that in the middle of the city, labor are problem, like costly, then we have to transport labor there. Then purification of raw materials and everything. So let's write raw materials, labor, purity of raw materials, purity of raw materials. Okay, continuity. Again, let's write the same sort of assurance of continuity. Raw materials has to provide continuously. Labor has to provide continuously. Raw material, labor, transport, energy source, just write with small letters, okay? And also, demand for the product supposed to be high. Otherwise, what is the point of making something? Last one is demand. Then again, wastewater and methods of waste management is important. So we have to find methods of disposing these non-usable byproducts. So we can go for recycling and everything. So let's write disposal of non-usable byproducts. Disposal of non-usable byproducts, comma, or slash, recycling. Recycling. With me, go with small letters. Otherwise, space wouldn't be enough. Strategies to prevent the additional environmental pollutants by the industry. One way is recycling. Recycling. Comma, use of renewable energy. Renewable energy. Like wind power, sunlight, solar power. So no environmental pollution. Next one is site of installation. So when we are installing our industry, we have to have a proper path to find everything like raw materials, labor, or maybe the transport, what kind of a demand is there, and everything. Let's say we are installing a garment factory, sorry, let's say a textile shop. So who can buy textiles? So we have to come to sort of a city center. We cannot do in the countryside, likewise. Okay, site of installation, raw material, labor, transport, easiness of access. Okay, next one is the nature of power supply. Power can come from fossil, solar energy, nucleic energy, biomass. Biomass you're going to do under this unit. And also the cost effectivity of this power supply, because the electricity we know is now too costly. Then the transport facilities and market, nature of probable accidents and strategies that can be adopted to prevent accidents. We're going to talk later. Government rules, regulation, and policies. They have all these different standards depending on the product. Let's say we are using water, drinking water, washing water, or water for other industries. drinking water and the consuming water is supposed to be 100% pure. So let's say we are using the washing, like, the household stuff. We don't want that much purity. Come, darling. Let's say if we need water to make soap, so we don't never think about these hygienic conditions. So likewise, whatever the final end use, it depends on what we need. That's right. Depends on type of production. Nidula, from the beginning, listen this, okay? Depends on type of production. Example, food and drug. Food and drug. Comma, environmental pollution. Environmental pollution. How many units are there? You have to bind them separately. It's too big otherwise. See? You can ask them to detach and bind them separately. Okay. So the disasters have happened in early life. Let's see a couple of. I don't know whether you guys remember in Sri Lanka, whatever the process, I don't remember what is the industry. They were using ammonia. They had this huge ammonia tank. Let's say the size of these 3 desk size, this kind of little big tank. So ammonia, have you guys ever color your hair? Or maybe your parents or sisters coloring, then that the strong smell that you feel. Oh, you guys know the ammonia smell? Every day you guys know that. Sort of our wee smell. Like in the morning when you, especially in the morning when you go to washroom, when we wee, the smell comes, that is little ammonia. Ammonia inhaling is really, really like harder, like it gives the dizziness and everything. So one person has just got fainted and fallen onto the tub. Died within seconds, okay, because he's then the swallowing ammonia. Another 2 people come and try to save him. All 3 has fallen onto here. In Sri Lanka, a couple of years ago that happened. Okay, so Sri Lanka, like a couple of very few people are dying. Let's see what's happened in these industries in other countries. Safety of the production processes and preventing of accidents are very important in chemical industry. For this, some of the disasters occurred in relation to chemical industries should be investigated. These are past. In 1921, 500 to 600 people died at an explosion occurs in Oppau of Germany. On is not there. On is not there, just cut on. The explosion was caused by 4,500 tons of a mixture of ammonium nitrate. You guys know we are using ammonium nitrate as explosives and ammonium sulfate meant to be used as fertilizers. They were using it as fertilizers. Similarly, Chernobyl nuclear power station, that is I remember this one when I was very, very small. I remember people were always talk about that one. That happened in 1986. It's not that old one. That's from Ukraine. Ukraine is really unlucky. Now they're having this war. And yeah, everybody knows that. Like your parents know that, then they are talking about it. Chernobyl. Yeah. And Ukraine is having this war. And very recently, Trump was, I don't know. Have you guys heard that? I feel like Trump is like being a big guy. I feel like what happened when a country like Sri Lanka, we poor country, if we visit him, how would he treat us to our president? Like he didn't respect, because the other guy, whatever the underlying story is there, but the Ukraine president, he was keep talking like Mr. President, Mr. President. But he didn't care that. He was just, see how this guy is wearing the like seven character. That's how I was feeling, like really disrespectful. So I'm worrying if someday our president is going to that country, what would happen? Anyway, so the Chernobyl is nuclear plant that is in Ukraine in 1986. Claimed nearly 4,000 human lives at once. In single second, 4,000 died. Because and another something, because of a Bhopal incident, that is India, that's in 1984, 8,000 people have died within seconds. And you know, if it is a nuclear plant, then the other, like during the Second World War, what happened to this Japan, that nuclear attack. So even today, they're having some sort of a little defects. So they are continuing that as well. So you have to be really, really careful. The reason of this was found to be the leakage of the highly poisonous gas methyl isocyanide for this Bhopal incidents. Therefore, it is very important, you know, the cyanide is how harmful. To understand properly and real need of chemical industry and political, social, economical, and environmental changes associated with it. Moreover, the understanding about the maintenance of the production process safely, efficiently, and effectively is also great importance. Now, you can understand why sometimes even in Sri Lanka, these people are doing this huge strike, picketing, and protesting and everything to avoid installing these big industries in Sri Lanka. Because Sri Lanka is a very small country comparing to India, Australia, America. Use of raw materials of chemical industry. Raw materials use other substance that are, if you want using a pencil or color pen or highlighter with me, you can underline. Or you can go home and you can listen this second time, or you can underline, whatever, you can go like that. No, not necessary. Nothing. So far, nothing you want to memorize. Oh, only this part. You need this part. Whatever we have, this the requirements to be considered. It is important. This introduction, these problems, not necessary. This part is important. What we are now reading. Raw materials are the substances that are supplied from outside of the chemical industry, which takes part in the production process. Production of compounds such as sodium bicarbonate, sulfuric can be given as examples for this. In some chemical industries, chemical components contained in raw material exist in the product as they were. Some industries, raw materials existing as it is. That is, chemical changes do not occur, but physical changes do occur. Sometimes chemically they are not changing, but physically they can be changed. Paint production is an example for this. Chemical nature not changing. Various raw materials are used for chemical industries. Different sources are used for this. For example, nitrogen gas is N2 gas in atmosphere, is used as one of the raw material to production of ammonia. In ammonia, we know to production of ammonia, we need nitrogen and hydrogen. Atmospheric air in the source from which this nitrogen is obtained. So to make ammonia, atmospheric nitrogen is using. Atmospheric air is first liquefied and nitrogen gas is separated by fractional distillation. We did that. And used for ammonia production. Okay, that is for ammonia. We need to separate nitrogen, then we use that nitrogen from atmospheric air. But in the production of nitric acid, instead of pure oxygen gas, again, our atmosphere has nitrogen and oxygen together. When they were using nitrogen for ammonia, they separate nitrogen, then they use it. But when they are making nitric, they need oxygen, but they are not separating oxygen. They are just using oxygen as it is. Instead of pure oxygen gas, atmospheric air is directly used to obtain NO2 gas to oxidize to oxidize ammonia. By oxidizing ammonia, we make nitric. For that, ammonia plus atmospheric O2 we are directly using. By oxidizing ammonia. In ammonia production, Haber process, though atmospheric air is the source of nitrogen, which is an essential raw material to obtain, in the manufacturing of nitric, atmospheric air itself is used as a raw material. Thus, facts such as the way the entire product process is planned, expenditure, and what level of purity should be maintained are useful to decide in which form the raw material should be used. if you can use it directly the raw material, so it's very cost effective. Less price is going there, but let's say that you are using normal atmospheric air to separate nitrogen. So we are going to the fractional distillation. So it is very costly and time consuming. When using a natural resource as a raw material, it is useful to take the flowing into consideration. Occurring in large deposits for long-term use. Let's say we are using calcium carbonate. So calcium carbonate is supposed to get continuously. Easy to reach. That's why we have to install our industry closer to calcium carbonate extraction, whatever the places. And then the purity. Especially crude oil is source for the production of many basic organic compounds. Hydrogen gas obtained by cracking of hydrocarbon, decomposing hydrocarbons, is used as an essential raw material for the production of ammonia. Okay, nitrogen from atmospheric air, fractional distillation, separate nitrogen. Hydrogen from cracking of petroleum oil. Hydrogen gas obtained cracking of hydrocarbon coming from this crude oil. Coke or the carbon is non-renewable. Okay, in this note, non-renewable and renewable, they were always like giving little more importance, because non-renewable mean you cannot get it or we cannot make it easily. So this is usually coming from these thousands of years, like, you know, the production of these fuels, like using fossil kind of stuff. So those are called the non-renewable. Raw material used for the production of iron. So iron production is little like challenging because coke is non-renewable. Okay, let's see how air is using. Oxygen is needed as an active component in iron extraction, production of nitric acid and sulfuric acid. Atmospheric air is used as a raw material in this production. Okay, but they are using a different ways for that. Atmospheric air is used as a raw material of nitrogen. Nitrogen gas obtained by liquefaction of air followed by fractional distillation is used as a raw material in manufacturing of ammonia. In the process of separating nitrogen gas from atmosphere, atmospheric air is used as a raw material. Okay, air. When using of atmospheric air for chemical industries, it could be identified as a source of nitrogen or gas. Normally, atmospheric air we usually use as a source of nitrogen or as a source of oxygen. Even it has carbon dioxide, we are not using atmospheric carbon dioxide. Usually, we can use carbon dioxide very easily from decomposition of calcium carbonate. So, only to get nitrogen and oxygen, we are going with this. Nitrogen and oxygen, underline that, okay? Atmospheric air is using for nitrogen and oxygen. Okay, air, we can compress, then we can get liquefied air. Through the fractional distillation, we are making nitrogen. And then from the crude oil cracking, we can get hydrogen. These two together make ammonia. That ammonia we can use for fertilizer and other industries as well. But that ammonia is again reacting with atmospheric air. That air has O2. With this ammonia, through the oxidation, we are making NO2 gas. Here again, another raw material is water, so we can make nitric. So air using different ways to get different products. Then water. Water is used for the production of sodium hydroxide and nitric acid, sulfuric acid, calcium hydroxide. For all these, they are using water. But depending on the production process and the product end product, sources are different. Seawater is not used as a source of water in these industries. Okay, even we need water, seawater has too many ions. So ions are interfering here. So we are not using seawater for production of these. The reason for this is that the various sources present in seawater interfere with the production process and also get into the products as impurities. Hence, it is very important to take care about the standards of the raw materials. Okay, but for the production of sodium chloride, what do? We need, this is a raw material. Let's say raw material is a sodium chloride. Sodium chloride is obtained using seawater as a raw material or from the ores of rock salt. You guys know Mexican has this dried sage, so you can use rock salt ores. Then the caustic soda is the sodium hydroxide is produced using sodium chloride. Okay, then this sodium chloride we're going to use as a raw material to produce caustic soda or sodium hydroxide. It is also used as a raw material in the extraction of sodium metal. To extract sodium metal, we are using fused pure sodium chloride. Seawater can be counted as a source for the production of sodium chloride. But seawater cannot be used as a raw material for the production of caustic soda of sodium hydroxide. See, sodium chloride, seawater is raw material. For caustic soda, sodium chloride and water is the raw material. Minerals. Minerals are renewable source. Why is that? Because those are, maybe earth crust has a lot, maybe sea has a lot. Sorry. If it is coming from sea, it's non-renewable, but if it's coming from earth, it is non-renewable. Renewable means we can reuse, we can remake. Minerals are non-renewable resources, just underline that. For the extraction of minerals such as iron, copper, nickel, aluminium, and titanium, minerals containing those metals are used as raw materials. Under our unit, we're going to talk about the titanium. Ilmenite for titanium, rutile for titanium, those are the minerals. Also, minerals containing phosphates are used for the production of phosphate fertilizers. As minerals are non-renewable resources, there could be a recycling process after using the production from minerals. Further, it is also important to use those products to produce useful substances that are long-lasting. Any non-renewable, if we're using any non-renewable, we're going to think about, because we never can make it back, the product's supposed to be long-lasting and we can reuse it or we can recycle that. So those parts you have to consider. Then coal is again a non-renewable resource. It is mainly used as a fuel. In extraction of iron, it is used as a fuel, a direct reductant as well as raw material essential to generate CO, which is major reducing agent for iron industry. These industries we're going to talk later again. This is a summary. Crude oil. Crude oil is a non-renewable resource. That's again non-renewable. It is used as a main material of fuels such as petrol and diesel. Crude oil is a main source from which raw materials for the production of monomers for polymers, medicine, and basic organic compounds are obtained. As this is a non-renewable resource, continuation of the production based on it become a problem with its consumption. Now that's why they are trying to find other fuel resources. Another crisis is the increase in global warming caused by the carbon dioxide. When you are burning any carbon product, it's releasing carbon dioxide. Carbon dioxide is a greenhouse gases which cause the global warming. We're going to do that later. During the burning of fuel obtained from the crude oil. Okay, plants. Plants considered as renewable, but we know it is only for a certain amount. Plants are getting like non-renewable because if you use them too speedily, it's become non-renewable. Okay. Plants are very important sources of the production of various oils, latex, rubber latex. Resin is again something coming from plants like latex and medicines. Plant materials are known as biomass. Bio mean life, okay? Biomass and used as a fuel for industries. Plants are also using industries as fuel, okay? You know, the firewoods as well. And also the raw material for the production of various organic compounds. As a plant is a renewable resource, it is a source that can be managed without disturbing the natural cycle in the environment. Industries which use petroleum oil to generate power have started to use biomass as an alternative source for energy. Industries in our countries too are inclined towards this. Okay, that using the biomass, production of biodiesel is one solution to avoid using of this crude oil, but this is again has some sort of like not always using the raw materials as natural or renewable, some sort of non-renewable we need for the biodiesel as well. Biodiesel is a topic that we're going to do under this unit. Okay, now we are going to different industries, okay? And in there, this is again, you make it a short note. Whatever the main topic, I'm writing raw materials here. Just let's write together, make that your short note, okay? So, raw materials essential for extraction of magnesium by Dow process. Let's first listen to this. Minerals containing magnesium is abundant in earth crust, but extraction of magnesium from seawater is more profitable. Other than sodium, magnesium is the most abundant cation in seawater. In seawater, about 0.13% by weight is magnesium. The solution discard at the last stage of producing salt from seawater is called the bittern. Okay, so what is a bittern? Bittern is the supernatant after extraction of salt. Okay, so that is the bittern. So this bittern now doesn't have sodium. It's already extracted so that it is rich with other minerals. So whenever we need to get other minerals, we are using the bittern. As bittern containing significant amount of magnesium ions, it is more suitable to use bittern to extract magnesium. Either seawater or disposable brine obtained from the reverse osmosis. Okay, what is the normal osmosis? Normal osmosis is concentration gradient going from higher concentration to lower concentration. Reverse osmosis means we have to extract magnesium. Let's say the magnesium concentration is increasing. So we have to forcefully get more and more magnesium to magnesium medium. So that's going from the lower magnesium to higher magnesium. That is the reverse osmosis. But here, through the reverse osmosis, that's an example, we can remove unwanted source, unwanted, whatever this, removal of unwanted materials, removal of unwanted materials, removal of unwanted materials. Okay. So before we are moving to the next topic, I want you to write here, these are the raw materials, and also to separate magnesium as magnesium oxide, we are using calcium carbonate to get calcium oxide. We're going to go through that. But before moving on, let's write here, bittern from sodium NaCl production. In front of the extraction of magnesium Dow process, let's write there, bittern from NaCl production plus CaCO3, calcium carbonate. Calcium carbonate. Okay, now let's see. There are a couple of steps that we're going to go through. There are actually 4 steps, okay? The step 1, what we are doing here is we get this magnesium, or we separate magnesium as magnesium hydroxide. So we need hydroxide. To get that hydroxide, we are using calcium hydroxide. To get calcium hydroxide, to get calcium, to get hydroxide, we are using calcium carbonate. So we burn calcium carbonate to get calcium oxide. Dissolving calcium oxide in water, we get calcium hydroxide. And you guys know, calcium, which out of calcium hydroxide and magnesium hydroxide, which is more water insoluble. Going down the group, solubility increases. So who's insoluble? Magnesium hydroxide. So magnesium hydroxide precipitate, we separate that one. So then we dissolve it in HCl. Then we make magnesium chloride. Then we dry that. We get the pure magnesium chloride. Then we go through the electrolysis if you want magnesium. That is a process, okay? That is a summary. Let's read everything leisurely, okay? So the step 1 is right in front of that. Production of calcium oxide by calcium carbonate. Write that. Production of calcium oxide by calcium carbonate. So next time when you read the note, you can understand nicely. Okay, let's read. The main aim of this step is the production of calcium oxide, which is obtained by the thermal decomposition of limestone. Dolomite also can be used for this purpose. So this is a limestone. This is a limestone right here. And it is giving this calcium oxide and calcium carbonate. But the next one, this is the dolomite. Dolomite gives calcium oxide, magnesium oxide, and carbon dioxide. Okay. As this reaction is reversible, see, these reactions are reversible. By designing the thermal decomposition process, carbon dioxide gas is efficiently removed. Contamination of calcium oxide with calcium carbonate is a disadvantage. Because to give the reaction go forward, we have to remove the product, so the reaction is going forward, but still, it has the equilibrium. Leaves a little part of calcium carbonate or the calcium carbonate and magnesium carbonate coming to calcium oxide. That is a disadvantage. Step 2. The object of this step is to produce magnesium hydroxide from solution containing magnesium 2 plus. So here you can write in front of step 2, let's write production of magnesium hydroxide. Production of magnesium hydroxide. Okay, production of magnesium hydroxide. The oxides produced in the first step, either calcium oxide or calcium oxide and magnesium oxide together, if you use the dolomite, react with the bittern solution. Okay, now this is reacting with the bittern solution, but bittern solution also has magnesium 2 plus water as well. Calcium oxide react with water to form calcium hydroxide. Calcium hydroxide dissolves slightly in water, giving calcium 2 plus and hydroxide, because if you remember, calcium hydroxide is partially soluble. Calcium hydroxide partially soluble, only part is coming. Since the solubility product of magnesium hydroxide is lower than that of calcium hydroxide. Okay, magnesium hydroxide need less hydroxide to precipitate comparing to calcium hydroxide. That's why calcium hydroxide existing in aqueous. Magnesium 2 plus ion in the solution are precipitated as magnesium hydroxide by hydroxide ion supplied by calcium hydroxide. With this, more and more calcium hydroxide goes into the solution, releasing OH minus without remaining calcium hydroxide as precipitate. It dissolves. The amount of calcium oxide required to the precipitate magnesium 2 plus ion in the solution is added. Precipitation of calcium hydroxide with magnesium hydroxide is a disadvantage. Okay, what we can do here is, this is totally the bittern solution. In the bittern solution, when we add calcium oxide, it has water. So it is reacting with calcium hydroxide. It is making calcium hydroxide. Calcium hydroxide is partially soluble. So in aqueous medium, so this is with equilibrium making this hydroxide. Then this hydroxide is reacting with magnesium to make magnesium hydroxide. So the hydroxide is using here, so that this equation is continuously going to forward. So more and more calcium hydroxide get water soluble. So we have to decide how much calcium oxide we add, avoid final product has this calcium hydroxide. Understood? Otherwise, this is a disadvantage. This is a final product we need, but it has calcium hydroxide. Okay. Step 3, reaction with HCl to make MgCl2. Reaction with HCl to make MgCl2. Reaction with HCl to make MgCl2. Magnesium hydroxide formed is filtered and removed and react with concentrated HCl to get magnesium chloride. So that's a double displacement, acid-base reaction. Anyway, you're going to get this salt. If burnt dolomite was used, calcium oxide in it reacts with magnesium ions in the solution as above. But as magnesium oxide is insoluble in water, see, maybe you would think having magnesium to extract magnesium oxide in extraction of magnesium is easier, but the problem comes here. Magnesium oxide is little more insoluble compared to calcium oxide. So magnesium oxide existing as it is if you use dolomite. So that's a disadvantage, okay? But as magnesium oxide is insoluble in water, magnesium oxide is mixed with magnesium hydroxide precipitation. Step 4, drying and electrolysis. Drying and electrolysis. Step 4, drying and electrolysis. Drying and electrolysis. The solution is heated strongly to vaporize water. Then it is dried so that the amount of water of crystallization become considerably low. The dried salt containing about 60% of water. Even if we dry, so this is hydrated. That water is get away by what? During the electrolysis, we provide high temperature too. So during that, it is getting away. First, solid formed is fused in the steel chambers where electrolysis is done and then it is electrolyzed. During heating for fusion, all the water of the salt gets completely removed. Okay, during heating, water gets away. This hydrated water gets away. The temperature of the cell is maintained within the range of 700 to 800. We have to melt down the magnesium chloride. For that, we have to use a little higher temperature than its boiling point. Since the melting point of magnesium chloride and magnesium metal are, okay, magnesium chloride 714, magnesium metal 650. So if we go a little above 714, we can melt magnesium chloride and also we can melt form magnesium as well. The temperature of the fused salt should be maintained above those melting temperatures. As magnesium metal formed during the electrolysis of the fused salt exists in the molten state, its withdrawal from the cell is easier. The density of the molten magnesium at its melting point is 1.584 and which is smaller comparing to the density of magnesium chloride, which is 1.68. So what happened? Magnesium is floating on magnesium chloride. So we can fix a little opening there to separate the floating magnesium, pure magnesium. Fused magnesium metal floats on fused magnesium chloride. Okay, so the reactions. We have only magnesium and chlorine. So magnesium is supposed to be reduced at the cathode and chlorine has to be oxidized at the anode. So the reaction of anode right here, oxidation, and that's positive. Right there, oxidation positive. And right here, reduction negative. Cathode, reduction negative. liquid magnesium formed is taken out from the cell. From this, about 99.8% yield of magnesium can be obtained. As the melting point of magnesium is above 650, it exists as a liquid at 700, which is the electrolysis temperature that we are using. Okay, if you go with the cross section, graphite anode, just write here positive. This is the graphite anode. And we are using here this this actually is the cathode, steel cathode actually, that is steel. Are they giving any cathode compound? Yeah, steel container. That's the cathode actually. So then they have holes here. Okay, at the cathode, magnesium 2 plus reducing to magnesium, but through these holes, they are coming to the top here. So using these outlets, from these outlets, we can separate magnesium. And also gas is anyway evolving and coming to the top. From here, through this, we can separate chlorine. And you guys have to practice to draw this. It's easy. This is the value tubes that supply fuel gases that for burning. This is those two inlets that introducing fuel. This is the steel cathode and this is the graphite anode. So molten this when this magnesium are coming out and floating here, so you can separate it from these inlets. Clear? Okay, strong and lightweight material are required for aircraft and vehicles. This is the uses. We have done uses earlier. Let's just read it. We have uses in inorganic chemistry. Magnesium metal is very important for the production of alloys to have this kind of properties. In this production, released CO is disadvantageous. Carbon dioxide is added to the atmosphere during the burning of limestone and dolomite. Combustion of petroleum fuel to obtain a higher temperature during the electrolysis, which causes this global warming and everything. So the last little part is to talk about the uses and then the environmental impact. Okay, now we're done with production of magnesium. That is exactly the same way that we're going to go one by one. Now you understand it is not hard. You can understand nicely and easily because now today, you guys watch this, read this. You guys listen to my voice. So today is the day that you're going to have the maximum memory. Before you forget this, just read this if it is possible tonight again. You guys know if you do not read this, 60% of whatever new things you forget. But if you try to memorize this today, then the next week it's going to be easier. Trust me, this is what these students are saying. Very, very talented students, they don't like Unit 14 because they are not doing this essay question from that. So they feel like less motivated to read this one. Don't do that. If you want 100 marks, you have to read it. Let's say otherwise, your total marks coming from 95 to something. Understood? 5 marks is losing. And then out of 45, something become your first paper marks. Don't let this happen, okay? Have the memory. Okay, we are done with that. So we're going to go with this second production. So we are moving to now the production of caustic soda, which is the sodium hydroxide. Let's write the raw material, conc NaCl aqueous. Conc NaCl aqueous in front of the topic. Highlight, underline, then the node become more familiar to you. It become your node. Now it's a photocopy. Make it become your node. Okay. A pure concentrated solution of sodium chloride is called brine. Sodium hydroxide is produced by electrolyzing a brine solution. This is little related to Unit 13 electrochemistry. We did this at the electrochemistry as well. As the byproducts, hydrogen gas and chlorine gas are released at the cathode and anode respectively. Okay, NaCl with water makes NaCl aqueous. This is the anode cathode electrolysis reaction. Okay, this is not a normal reaction. So NaCl plus chlorine, if you hydrolyze, we're going to get right here this from anode, Cl2 from anode, H2 from cathode. Show those two. Cl2 anode, H2 cathode. No need. Use a pen. It's okay, leave it there. From the next part on, use couple of color pens. Summarization one color, writing information one color, maybe the raw material the color. Just use a pen. Okay, when 2.25 metric tons are produced from the solution containing 50% weight to weight caustic soda, nearly 1 metric ton. How much kilograms? How many? Ton, 1,000, just right there. Yeah, I have written 1,000 kilograms. 1,000 kilograms. Okay. 2,250 kilograms gives 1,000 kilogram chlorine, 30 kilogram hydrogen. So that's easy comparison. If this is 1,000, you have 2,000. This one become 2,250 kilograms. Gives 1,000 kilogram chlorine and 30 kilogram hydrogen. Clear? Though there is a consequent difference by the mass like this, when the amount of moles are considered, the amount of moles of chlorine and the amount of moles of hydrogen are approximately equal. See, if you go with the mass of chlorine is greater because its molar mass is high. So this one you can write here. This is, you can write it here, 1,000 kilogram, and here 30 grams. And here you are using 2,200. Let's write that. That's easy then. On under NaCl, let's write 2,250 kilograms. Under chlorine, 1,000 kilogram. Under hydrogen, 30 kilogram. Here. Okay. So they say even the mass goes this way. If you divide mass by the molar mass, number of moles supposed to be 1:1. It's supposed to be 1:1. Since chlorine gas can slightly dissolve in aqueous reaction medium, comparing to H2, chlorine dissolution is high. So the collected amount of chlorine, if you go with the number of moles, it is less comparing to hydrogen because chlorine is more water soluble. Okay. The cell used to produce caustic soda by electrolysis. There are 3 different kinds of cells which are called chloroalkali cells. 3 different types: mercury cell, diaphragm cell, membrane cell. We're going to talk a little about mercury and diaphragm, but more effective is the membrane cell, which we are using today. And most worst case of this mercury cell is, it is contaminating. Sodium hydroxide we are making is contaminating with mercury. So that is the main disadvantage of mercury cell. Just write there, contaminated by mercury. Contaminated by mercury cell. Okay. A little explanation of this membrane and diaphragm, mercury and diaphragm are going here. Let's read. Earlier, production of sodium hydroxide was based on the mercury cell method. However, possibility of releasing mercury to the environment and contamination of sodium hydroxide with minute quantities of mercury are its main disadvantages. The basic basis of membrane cell and diaphragm cell are almost identical. The major difference is that in the membrane cell, instead of a diaphragm, a membrane permeable to sodium ion is used to separate the anode and cathode. Diaphragm and membrane. Here we are using a membrane rather diaphragm. Okay, diaphragm is like, the asbestos diaphragm, so on. Membrane is very thinner, and also it is permeable to sodium. Compared to the membrane cell, in the diaphragm cell, the liquid level in the anode chamber is above the liquid level of the cathode. Okay, anode and cathode. Anode liquid level is greater comparing to cathode liquid level. So this has higher mass and higher density and higher pressure. Going from here to here, a salt moving from here, anode to cathode become then easier. Therefore, a hydrostatic pressure comes with water, is exerted from the anode chamber solution to the cathode chamber solution across the asbestos diaphragm occurs. This hydrostatic pressure affects the migration of sodium ion from anode chamber to cathode chamber. So from anode to cathode, then sodium is passing. It also prevents the movement of hydroxides from cathode solution to the anode solution. So anode is and cathode here. Anode going from here to here, sodium gets here. Cathode chamber, we are adding water. Electrolysis, it is giving OH minus. So sodium plus coming from this side, OH minus not going here, so that we can separate sodium hydroxide. But in the membrane cell, the anode is separated from the cathode by a membrane that permeable only to the movement of positive ions. Higher purity of sodium hydroxide produce lesser consumption of electricity and minimal impact on the environmental are advantages of membrane cell. Okay, underline those parts. Those are the advantages of membrane cell. So that we are going with the membrane cell method. We are not going with the mercury or diaphragm method. Even diaphragm method is all right, that you guys know that even other cations can also go through the diaphragm. The factors included in association with the cell are used for caustic soda production, applying cell potential, current density, sodium hydroxide production. See, the highest come from membrane cell diaphragms. Sodium hydroxide percentage, highest coming from mercury cell, but it is like the environmental pollution and itself, it is getting polluted sodium hydroxide. So we are not going with that. So we are going with this membrane cell. Even the product percentage is less. Okay. Okay, we're going to move on to the membrane cell method. Okay. Look at this. We have sodium chloride plus only water. So usually we are using, you can write together with me, we are using 26% sodium chloride. When it comes to 24%, we remove that. Understood? 26% NaCl, 24% NaCl. Okay. So, anode, oxidation. So, out of NaCl, see, this is the anode. You can write over there also the oxidation. Anode oxidation, cathode reduction. Okay, anode oxidation, cathode reduction. And this is anode. Okay, I'm going to go with the anode part. Anode oxidation. So you have NaCl here, Na plus Cl minus, and then Na plus, and then Cl minus oxidized to Cl2, then emits from the anode. So anode emits Cl2. Okay, anode emits Cl2. Then in the cathode chamber, we have only adding water. We are only adding water here. So cathode chamber has only water, and that is a reduction one. So H plus and OH minus is there. H plus is reducing to H2. Clear? Okay, so now this side has sodium plus this side has OH minus. Understood? Then this membrane is permeable only to cations. Only one single cation we having is now sodium going from here to here. This side is now only having this OH minus because H plus is here. So that the most pure sodium hydroxide making here, we can separate them out here. There. Okay, that's the process. Okay, let me read this one. Anyway, we have to read everything. Membrane cell method. The brine that is used in the membrane cell method should be very pure. Presence of magnesium, calcium, and sulfate ions in brine hinders the product process, disturbing the product process. Precipitation of these cations when the solution becomes basic disturbs the cell action, lowering the purity of, because medium, when the medium become basic, all these can precipitate as hydroxides. So to avoid that, we're going to remove that before we start the process. Caustic soda, because of the addition of these ions to the sodium hydroxide solution, is also disadvantageous. Therefore, the concentration of these ions impurities in brine water that is used for the production should be very low. Salt extraction from the seawater contains these three, magnesium, calcium, and sulfate. So that chemical treatment needed to remove them, what we are doing is to remove magnesium, we are adding magnesium hydroxide. So the hydroxide, sorry. To remove magnesium, we are adding sodium hydroxide. Sulfate ions can be precipitated as removal by barium sulfate by adding barium chloride, magnesium and calcium sulfate by sodium hydroxide and sodium carbonate. Okay, so we are adding barium chloride, sodium hydroxide, and sodium carbonate. Sodium hydroxide for magnesium, barium chloride for sulfate, barium sulfate, and then calcium carbonate. Sodium carbonate is to calcium carbonate. Clear this? Okay. So you can highlight these three other things we are adding. Barium chloride, sodium hydroxide, and sodium carbonate are the three compounds we are adding externally. Barium chloride, sodium hydroxide, and sodium carbonate. Okay. Then the cell. Okay. At the beginning, the solution in the anode chamber mainly contained Na plus and Cl minus ions. Very small amount of H plus and OH minus ions formed by the dissociation of water. The standard electrode potential required for oxidize OH minus at the anode to give O2 is 0.4. Where the standard electrode potential of oxidizing Cl minus at the anode to the liberate Cl2 is 1.36 positive. Hence, there's a possibility of liberating O2 because this is less positive or negative. So that's possible to oxygen to removal. That's also possible. Okay. Several precautions have been taken to minimize releasing of O2. So what they are doing is they minimize hydroxide amount to avoid that. Okay. So this is the hydroxide which can release O2. This is the Cl minus which is releasing Cl2. NaCl concentration in the brine used to produce caustic soda is relatively high. So they are using more Cl minus rather more OH minus. So when the medium having more Cl minus, it tends to oxidize. Clear? Rather OH minus is oxidizing. Concentration is very low and the Cl minus concentration, OH minus concentration is very low, Cl minus concentration is very high. Probability of forming an oxygen molecule and two water molecules by combining 4 OH minus ions in the electrode is relatively so that low. Since there is a relatively higher concentration of Cl minus ions in the anode chamber solution, the ability of forming Cl2 gas by the oxidation of Cl minus are relatively great. Since the concentration of Cl minus is greater, formation of Cl2 is also greater. With the electrolysis, when the Cl minus ion concentration decreases, there is a chance for the oxidation of OH minus ions liberating O2. Because of this, concentrated salt solution is continuously pumped. That is the reason. Because of that reason, we are not letting this to go less than 24. If it is less than 24, there's a chance of oxidizing OH minus. That's why continuously introducing and removing this low concentrated Cl minus. MCQ, you need to understand those for MCQs, okay? Continuously pumped into the anodic chamber, and anodic chamber solution is continuously removed. Though the Cl minus ion concentration in the system decreases, sodium plus ion concentration does not. No. There is no cleared, but all the questions starting from 2002 to 2024, this industrial and environmental pollution, this unit, all the questions I'm doing for full papers. Because I have the tude, but the thingy is they have done like, you know, the more than 90% of all syllabus and new syllabus after 2019 is different. So I have the tude and answers and everything, but those are now out of syllabus. You don't want that. Don't worry, we don't want tude. Everybody do this only with this note. Very easy to memorize. Remember, I asked you guys to keep your inorganic note by the side of the bed. So even when you are kicking, you know, so keep the same in the bed. Okay. The only feeling tired or something. Okay, let's get the break at 10. I want you guys to be really alert because I'm going a little faster so you can absorb nicely when you're alert. When the entire cell is considered, maintenance of electric neutrality in the system is a fundamental feature. So, when chlorine ions are given off from the anodic chamber as Cl2 gas, either another negative ion should come into the anodic chamber solution or sodium plus ions should migrate into the cathode chamber solution. Because now Cl minus decreasing, sodium plus supposed to be decreasing, so that is a tactic they are using. Reduction takes place in the cathodic chamber. H plus ion is more easily reduced than the aqueous sodium plus ions. At the beginning, the medium in the cathodic chamber has no sodium chloride, so its main component is water. Since H plus ion resulted by the dissociation of water molecules at continuously reduced and equilibrium maintained by the reversible dissociation of the water molecules drops, because now H plus is decreasing, OH minus is now high, water is less. Since water molecules continuously dissociate, with the removal of H plus ions formed by the dissociation of water as H2 molecules, OH minus ion concentration in the cathodic chamber increases. When electrolysis is carried out continuously, OH minus ion concentration in the cathodic chamber rises with time. Now, okay. This unit has a lot of like repetitive words, repetitive sentences. So you can understand this really nicely. Same thing, repetitively, many times explaining in this note. Okay. The equilibrium brought about by the dissociation of water molecules can be shown here. You guys know this. Yeah? Okay, when you remove H plus, reaction is going more and more to forward to give more OH minus. The situation where the equilibrium is lost during the reduction of H plus to H2, so this reaction occurs. Okay, he has explained this equilibrium concept very like descriptively and repetitively Even for very weaker student can understand this. In the cathodic chamber, H plus ions get reduced to H2 molecules at a rate equal to the rate of oxidation of Cl minus ions to Cl2 in anodic chamber. So formation of H2 and formation of Cl2 speeds are same. Because of this, the rate of which water in the cathodic chamber continuously dissociate generating OH minus ions is equal to the rate of decreasing Cl minus ions in the anodic chamber solution. Thus, the entire system is electrically neutral. Along with the electrolysis in a membrane cell, though the concentration of Cl minus ions in the anode chamber decreases, sodium plus ion concentration does not decrease. Meanwhile, in the cathodic chamber, OH minus ion concentration increases because of the reduction of H plus ions formed by the dissociation of water. This develops a potential difference across the membrane. If OH minus ion in the cathodic chamber pass into the anodic chamber, they react with chlorine in it. So they have to avoid also the OH minus come back to this cathodic anodic chamber, because in anode now we have Cl2 producing. So that can react with OH minus. So the membrane is only permeable to sodium plus. It is impermeable to OH minus as well. It's very selective membrane, yeah. But in the case of membrane cell, OH minus ions are not capable because it has this negative force. So it is repelling negative OH minus to migrate across the membrane. So it reacts. So this reaction does not occur in cathodic chamber. In the membrane cell, the anodic and cathodic compartments are separated by a membrane permeable to positive ions. Here the only example is sodium plus. This membrane has very tiny pores and negative ions are bound to the borders of these pores. The negative electric field in the space around the pores attracts positive ions towards the pores and repels negative ions, while water is continuously added to the cathodic chamber by an inlet tube, which the solution contains sodium hydroxide is removed by the outlet. So can you understand how this, not only this inorganic chemistry part, but also this electrochemistry knowledge they are using to produce sodium hydroxide. Sodium hydroxide is one of the main ingredients in soap production. There are a lot of things going on, understood. So these researchers have done all this. Chemistry is the most important thing in the world. Even the doctors are using all those chemicals, drugs that, the chemists are producing them. Okay. Anode is made of titanium and cathode is made of nickel. Possibility of carry out the sodium, because titanium is inactive towards chlorine. That's why this is expensive. Sodium hydroxide process continuously is a special feature. Brine with concentrated 26% of continuously pumped into the anodic chamber, and as shown of the flow chart, the concentration of the solution removed, concentration in the solution removed from the anode solution has dropped about 24%. In the anodic chamber, when the generation of Cl2 by the oxidation of Cl minus ions, H2 are formed by the reduction of H plus ions in the cathodic chamber. Repeatedly, he's saying, understood? Try to get this. You don't want again to read this one. While you go through this one, you understand very nicely this. Comparing to the increasing of the hydroxide ion concentration of the cathodic chamber, sodium plus ions existing in the anodic chamber move to the cathodic chamber. Therefore, a concentration of sodium hydroxide builds up in the cathode chamber, concentration of cathode chamber increasing. With the movement of sodium plus ions, an electrical neutrality is brought about in each chamber. Again, they are saying the same thing. This process continuously occurs during electrolysis. The Cl minus ion in the anode chamber do not move into the cathode chamber. Again, they are saying through the membrane. Hence, NaCl does not get mixed up with the impurities of sodium as impurities of sodium chloride. Anode and cathode reactions are very easy. Overall reaction that we even earlier talked about. Again, they have explained everything using this flow chart. So we're going to get this pure sodium chloride salt. Only it has Na plus and Cl minus. To that we are adding water. So that we are making the brine solution. Then we are adding barium chloride, sodium carbonate, and sodium hydroxide. Okay, to remove even if we have traces of these calcium, magnesium, and sulfates. And now we have pure brine solution in this side here. Barium chloride, sodium carbonate, sodium hydroxide. And the other side, we have this liquid Cl2. Sorry. And then we have this pure brine solution. Then anodic chamber, we have the brine solution. And that's 26. And when it becomes 24, we are removing it, but we can mix it with pure brine solution after recycling by adding more and more sodium hydroxide there. Then the electrolysis, anode and electrolysis, it is giving Cl2. Drying, removal of water, we can make Cl2 gas for the production of HCl. That HCl can make magnesium chloride to make magnesium, remember? So there are different ways we can go on. And also, here, separately you have the cathode with water. So releasing of H2 from cathodic chamber. And also from anodic chamber, we are having this OH minus here. That OH minus, then adding with sodium coming from this anodic chamber. Together we are making sodium hydroxide. By evaporation, we can reach whatever this expecting, whatever. Then soap, textile, whatever we're going to use, this sodium hydroxide. Clear? Okay, then the uses and then the environmental part. Uses of sodium hydroxide and byproducts. Uses of sodium hydroxide, soap, paper, artificial silk, dye, and also we directly using as a strong base, and we can precipitate heavy metals using sodium hydroxide. Chlorine, bleaching, textile, wood and paper, drinking water purification, production of HCl, chlorine production, production of chlorinated rubber, insecticides, dyes and medicines, vinyl chloride to make PVC, so on. Hydrogen, HCl, ammonia, hydrogenation of vegetable oil needed to make margarine, and also we can use hydrogen as a fuel as well. Okay, it's 10. Let's go to the break and continue. Okay, it's 10:04, 10:05. Come back at 10:20. Okay. Hello. Hello. I'll explain. Yeah, what is it, darling? Tisari. Oh, Tisari mean the English medium 26 Tisari. Come on, darling. When you are talking, I was like, you are like a new student. Okay, what is it? Okay. Sure, darling. Sure. Okay. Huh? Okay. WhatsApp me. WhatsApp me, then I'll send the link. Okay. Bye, darling. Okay. How come she's not just asking me the link? New students. Come back soon. Don't take too much time. Yes. Huh? At the end. Okay, so the next topic is production of soap. For the production of soap, we are using the raw materials. From plants, we can get oil. From animals, we can get fat, plus sodium hydroxide, or we are using potassium hydroxide as raw materials. Just write them down. During the manufacturing of soap chemically, triglycerides are subject to a hydrolysis reaction with caustic soda, that is called the saponification, forming glycerol and sodium salt of long-chain carboxylic acids. These salts are known as soap. A soap molecule comprises a hydrophobic tail. So this is the hydrophobic tail part of carbon and hydrogen atom and a side with a hydrophilic head. This is the hydrophilic head which reacts with or dissolve in water. The hydrophilic head contains sodium or potassium ion. If you use sodium hydroxide, that's sodium. If you use potassium hydroxide, that's potassium. And COO minus ionic group. I've started. Animal fat or plant oil is the one raw material for the production of soap. The other raw material is sodium hydroxide or potassium hydroxide. Okay, for the we are in the soap production because we have only like less than 8 hours. Otherwise, we have to go with three days. Okay, so the hydrophobic tail and hydrophilic head. Soap production goes with oil, fat, sodium hydroxide, and potassium hydroxide. Okay. Soap is manufactured by two processes, hot process and the cold process. In the cold process, soap and glycerol are not separated. Glycerol is deposited in soap. Here, only the hot process and its four main steps are considered. Saponification is the main reaction between oil and sodium hydroxide. Then removal of the byproduct and also the glycerine. Purification of removal of all the other impurities, and then the finishing touch, like, you know, the color, smell, and everything. Okay, so before we moving to talk about this production, so this is the summary. Look at here, you can understand. Okay, it's in the recording. Okay, go with that. So this is the whatever the triglyceride, we say animal fat or plant oil. So that we are mixing sodium hydroxide. Okay, with organic chemistry, you guys know this is an ester COO. So these bonds are breaking here. So that this part, RCO, is reacting with this ONA, which is the soap. This is the soap part. Then this part is separating OH-H2O, OHCH, OHCH2. This part, tri-OH group. So this is called the triglycerol, sorry, glycerol or glycerine. So three here, so that's why we call it the triglyceride. So this R can be any of these compounds, clear? So this is then the soap. So the soap is esterification, which we call the saponification. Okay, this part you don't want if you write this percentage in a side. Understood? Okay, when you are going together, you can write those. When I'm reading, I'll show that little. I'm showing it here, so you can go together. Okay, now let me read the note first. I don't want to go with small letters. The number of carbon atoms in a soap molecule varies as 12, 14, 16, and 18. In coconut oil, lauric acid, myristic acid, stearic acid, and oleic acid are bound by ester bonds in the triglyceride. The amount of long-chain carboxylic acid or fatty acid present in the form of triglyceride is indicated as a percentage. In addition to this, a small amount of fatty acid occurs as free fatty acids without forming ester bonds. In coconut oil, 44 to 52% of lauric acid is present. The number of carbon atoms in it is 12. 11 atoms out of them are the hydrophobic tail. One comes with COO, which is reacting with water, so we call it hydrophilic. The percentage of myristic acid in coconut oil is 14% and it contains 14 carbon atoms. Palmitic acid, which has the 16 carbon atoms, and the stearic acid, which has the 18 carbon atoms, percentages are 8% and 3% respectively. Oleic acid, which having 18 carbon atoms, ranges in 5 to 8%. Soap production using coconut oil is a mixture of sodium salts because they have different carbon long chain carbon length, so they have different acids. So I have made this little short note so you can forget that total paragraph. Lauric 44 to 52, myristic 14, stearic 3, oleic 5 to 8, palmitic 8. And also the carbon number. Lauric 12 carbon, myristic 14 carbon, stearic 18 carbon, oleic 18 carbon, palmitic 16 carbon. L 14, 18, 18, 16. 18, 18, 16. Okay. To removal of pigments and impurities in oil, it is sent over a special type of clay referred to as active fuller's earth. They have more pores so they can absorb all the dirts. Its temperature is mainly at about 90 degrees Celsius. After removal of clay particles in oil, it is used to make soap. Soap production can be conducted either as a continuous process or a batch process. Batch process is a traditional method. It is, in it, all the amount of raw materials are added together to the reaction chamber and allowed to react. One batch done, second batch done, third batch done separately. A batches of soaps made separately. Afterwards, the products are separated. In the continuous process, reactants are continuously supplied to the reaction chamber and products are continuously removed. Number 1, saponification. Here, purified vegetable oil or coconut oil is mixed with a solution of aqueous sodium hydroxide and heat. The purified vegetable oil or coconut oil and the caustic soda or sodium hydroxide solution or the caustic potassium hydroxide solution are pumped into the reaction chamber. Dissolving of caustic soda in water is exothermic. Therefore, dissolving a caustic soda in water is done as a separate process because it's increasing temperature. Oil and aqueous sodium hydroxide are two immiscible phases because they are not mixing with each other, so continuous stirring needed. Glycerin and soap are formed as a result of saponification. So this is the glycerin part and this is the salt part. This reaction is called the saponification. Reaction taking place at the interface of these two layers. Since sodium hydroxide is neutralized here, heat is produced. The temperature of the reaction mixture is about 70 degrees Celsius and mixture is mixed well. Oil divides into tiny droplets and increases surface area. Therefore, reaction occurs uniformly throughout the entire volume of reaction mixture. Okay, now we've done the reaction. Now we're going to remove this main byproduct, the glycerin. Removal of glycerin. In the aqueous phase obtained after saponification, basicity has dropped. Glycerin and a certain amount of soap have dissolved in the aqueous phase. Soap molecules dissolved in the aqueous phase are ionized and maintain an equilibrium as follows. See, soap is showing this equilibrium. To decrease the solubility of soap, in the aqueous phase, NaCl is added. So we are in sodium chloride. So this is going backward. So dissolution of this in water become less than. So you are making more and more. Reaction goes to this direction to increase the soap amount. As the sodium plus ion concentration is high, the above equilibrium shifts to the left and the soap molecules separate from the aqueous phase. Glycerin dissolves in the salt solution. Density of the aqueous phase increases due to the addition of NaCl. Okay, when you add more and more sodium chloride, the density of water body increasing, so soap become float on that. After separating impurities soap from the aqueous phase contains glycerin is pumped out. Okay, if you separate soap part, then we can separate the glycerol part separately. Glycerol or glycerin. Pumping of crude soap is easy because the temperature is 70 and crude soap contains a considerable amount of wetness. So you can, as a liquid, you can get away the soap. The aqueous salt solution removed from the reaction chamber contain glycerin. Okay, now the glycerin plus salt mixture is separated and water, so the soap part is separated because of its density. Thus, it is a good source to obtain glycerin. This aqueous salt has the glycerin. Adequate sodium chloride is added again to the solution obtained after removal glycerin and recycled. Okay, that again and again adding the sodium chloride to the mixture, we can remove the glycerin and we can add that back because that has also the sodium hydroxide as well. This salt solution is used to remove glycerin in impure salt. Salt solution we can again use to remove if you have more glycerin, like the solvent extraction method. So that kind of a method we can use continuously to remove the glycerin from soap. In this salt solution, though glycerin dissolves, soap does not dissolve. Okay, that sodium chloride solution is now thicker, concentrated. Glycerin is dissolving, but soap does not dissolve in that. Here, mixing soap well with the salt solution is very important. By this, crude soap can be purified to a certain extent, removing the glycerin remaining in it. Then the salt solution contains glycerin and soap, partially purified and separated. Then the two parts, salt solution plus glycerin one side, soap another side, we can separate. Once you separate, we are moving to purification. Water and sodium chloride salt are present in the soap, which is purified into a certain extent by removing glycerin. Wet soap, which salt is centrifuge. Wet soap with salt is centrifuge. You know the centrifugation, like rotating or spinning power separate with their mass or densities. When the aqueous salt solution separated from soap, then you can, like that, you can separate soap. The sodium chloride content in soap decreases. Yeah, you have to decrease sodium chloride to 0.5 mass to mass to get good soap. Presence of caustic soda in soap is harmful to the user. Yeah, having sodium hydroxide is harmful. Soap with high caustic soda content can severe damage the skin and tender tissues of eye. Therefore, citric acid, phosphoric acid, or free fatty acid associated with coconut oil are added to neutralize sodium hydroxide, which may be present even in minute quantities of soap. Usually, I'm not comfortable with soap. As far as I know about soap, just use the face wash, not soap. I don't use soap. Long ago, I have stopped. I'm using soap only to sometimes to wash hands. Okay, the finishing part. It is essential to remove water in soap after removing salt. To reduce the water content in soap to 12%, soap heated to about 120 degrees Celsius is displayed into a low pressure zone in the form of small droplets. Okay, what happened is you have this forming, let's say a cylinder, then you are spraying soap liquid onto that. With that temperature, water is evaporating, so you get solid soap. Same way they are making from liquid milk to milk powder, same process. As heat is absorbed for the vaporization of water, the temperature of the droplets decreases. While water vaporizing is removed, soap settles down in the low pressure vessel. Dry soap is then separated. Finished soap is made by mixing fillers, colors, perfumes, and molded into required shapes. Total fatty matter value of soap, TMF. This is sometimes going in these commercials. Total fatty matter, TMF, means the total fatty matter present in soap. It is the percentage of this sodium carboxylate or soap present in a cake of soap, this solid soap bath. The TFM value of a cake of washing soap is 54 to 56%, and rest is fillers, colors, substances which promote the clearing action of coloring. Clearing action and coloring. A disadvantage of soap is not dissolving and not lathering in hard water. You guys know what is hard water? Hard water having calcium, magnesium. See, hard water having these plus carbonates, bicarbonates, so they get precipitates. So let's say this M is calcium. So calcium carboxylate get precipitate, not like sodium carboxylate. So that's why they are not making enough soap forms. Reason for this is reaction of soap molecules with cations cause for the hardness and get precipitated. Detergents do not precipitate in hard water. The main ingredients of the artificial detergents are sodium alkyl benzene sulfonate. These cannot precipitate with these cations. This is a alkyl benzene sulfonate, this detergent. Okay? Cleaning action of soap. Dirt is a mixture of dust particles and organic compounds gathered around on a layer of oil. As the surface tension of water is high, dirt doesn't remove only with water. Soap lowers the surface tension of water and improves its clearing action. Decreasing the surface tension. So it lets the dirt get away from the, this is a substance. Let's say this is a substance. Let's say you have this dirt on that. So you're adding soap. What happens is, if this is water soluble, then the head goes in. If this is water insoluble, let's say organic, then the tail goes in. So tail makes more stronger bonds. So this whole part is getting away from the whatever the substrate. This is called micella or micella. The whole thing. Okay, that's all with soap. Number 4, production of sodium carbonate, solvay process, ammonia soda process, raw materials, sodium chloride, calcium carbonate, ammonia. Sodium chloride, calcium carbonate, ammonia. And you guys can see in this sodium carbonate, you don't see ammonia. Understood? So it's recycling. We are using it and we are recycling it back, making it back. Okay. So these are the main reactions because we need to dissolve carbon dioxide readily in water. That's little, like it's okay, but it's little harder. So what we are doing is, very first we dissolve ammonia in water. So now this is basic water. On that basic water, we can dissolve carbon dioxide easily. For that part, we are using ammonia, not to make the final product. Then to this ammonium bicarbonate, we are adding NaCl, making sodium bicarbonate. But when you heat it, from that you can get sodium carbonate. Clear? Okay, that is a summary. Sodium carbonate is a raw material required for a number of chemical industries. Therefore, sodium carbonate production is a major chemical industry in the world. Presently, about 20 million metric tons of sodium carbonate are annually produced in the world. The main chemical reaction involved in the production of sodium carbonate are given below. Okay, so this is reactions. Ammonia, essential for the production of sodium carbonate, is obtained by the Haber process we're going to do later. CO2 is produced by the thermal decomposition of limestone. The other main raw material is purified concentrated sodium chloride solution by removal of, again we're going to remove calcium, magnesium and sulfate. This is referred as the brine. Okay, so this is the production of calcium carbonate. He burned the calcium carbonate to get calcium oxide and carbon dioxide. The basic steps of the process occurs in specially set up tower for the production of sodium carbonate. Okay, so there are two steps. There are actually, yeah, 4 steps. Okay, 4 steps. Okay, first step is the ammonification. First, so we are going with the concurrent method. Brine is percolating down, ammonia is going up concurrently, so they are mixing. So we can get the ammonical brine. Then to that we are mixing carbon dioxide. First step is the ammonification. First, the brine solution is introduced from the top. The tower of ammonia gas is of the tower, and ammonia gas is introduced from the bottom of the tower. Mixing reactants efficiently by sending the reactants in opposite direction is referred to as the concurrent principle. Ammonification of brine is an exothermic process, so that if the temperature of the brine increases, efficiency of dissolving ammonia decreases. It is important to maintain a lower temperature in the tower by removing the heat in the tower through heat exchangers. Okay, that diagram is easy. Second step, ammonical brine, addition of carbon dioxide is the carbonation. Here you can go with this little summarization if you want. Here I have written like brine and ammonia mixing concurrent. Brine, ammonia mixing concurrent. Ammonification is brine, ammonia mixing concurrent. Then the next one is ammonical brine and CO2. Again concurrent. Ammonical brine, CO2. The brine solution saturated with ammonia is introduced from the top of the second tower, while CO2 is introduced from the bottom. Here, the reactants efficiently mix under the concurrent method. Again, they explain. Ammonified brine is basic medium. CO2 is an acidic medium. Dissolution, dissolving it in water is exothermic, hence forming ammonium bicarbonate by reacting aqueous carbon dioxide with ammonium hydroxide is also exothermic. For this also keeping the keeping the second tower cool is very important. In the first tower, you are mixing brine plus ammonia. Second tower, this is the second tower. So you are mixing ammonical brine with carbon dioxide. Ammonia is readily soluble in water, but the solubility of carbon dioxide gas in water is relatively low. The concentration of bicarbonate ion formed by the dissolution of carbon dioxide in water is very low. As ammonification proceeds carbonation, CO2 gas is absorbed well into the basic ammonia solution. This produces a high concentration of bicarbonate ions. That's why first we are using ammonia. And now we have formed this ammonium bicarbonate. Let's separate. So the number 3, separation of sodium bicarbonate. As ammonification brine solution is carbonated, the concentrated ammonium bicarbonate in the solution is increased. Since this brine has a high concentration of sodium plus, sodium bicarbonate crystallizes. Okay, usually sodium bicarbonate is an aqueous solution, very water soluble, but we are increasing its ionic product greater than Ksp. Just show that. Now the ionic product of sodium bicarbonate is greater than Ksp, so it is dissolving. Exceeds the saturated limit, that is the ionic product is greater than Ksp, so that making this solid sodium bicarbonate. The solid sodium bicarbonate that forms is removed from the solution. The overall reaction is for forming of sodium bicarbonate can be written as, okay, this is not a one single reaction, but as a one single reaction, we can show like this. You guys have to write reactions just to get memory. Okay, now we have sodium bicarbonate. Now we need to get sodium bicarbonate by heating that. Anhydrous sodium carbonate, by heating this, so formed CO2 gas is using for the recycling. So this is a reaction of heating of sodium bicarbonate to get sodium carbonate. This is easy. I just need to give you guys a little idea. Ammonium chloride, which is a byproduct of this process, is also used to regenerate ammonia as follows. For this, ammonium chloride solution is reacting with calcium oxide obtained by the decomposition of limestone. So the calcium oxide we are not throwing away. That calcium oxide reacting with ammonium chloride to get this ammonia again. This calcium chloride also this is the one single byproduct. Then we can use this calcium chloride for these, the desiccant, fertilizer, and so on other uses. Ammonia formed by passing the ammonifying tower according to the overall theoretical reaction for the entire process is follows. Okay, so this is the production of calcium carbonate, sodium chloride gives the calcium chloride and sodium carbonate. This is the final. This is not happening really, but we can show using the raw materials. We can separate the sodium carbonate. Calcium chloride is the only byproduct. Final product is this one. Let's write here desiccant, fertilizer, desiccant and fertilizer with ammonium sulfate, fertilizer with ammonium sulfate, NH4 twice SO4. Due to the following reasons, Solvay process is economically profitable. Number one, sodium chloride, calcium carbonate, both are very easily, cheaper, cost effective. Ammonia is not consumed and can be used. Okay, ammonia recycling, that's again cheaper. Part of CO2 is also recycling or reusing. Solubility of, okay, so we cannot use the same method for potassium bicarbonate because going down the group, solubility is increasing. So the potassium bicarbonate is more soluble. So we cannot separate the solid potassium bicarbonate. Uses of sodium carbonate, removal of hardness of water, addition to improvement cleaning action of the production of soap and detergents, washing soda production, to make wood pulp in paper industry, production of glass we are also using. This one, let's write. Uses in a side, you can write uses of sodium bicarbonate, NaHCO3. To make baking soda, uses of sodium bicarbonate, NaHCO3. To make baking soda. In fire extinguishers, to make medicines, as racing agent in food processing, Okay, Solvay process as racing, R-A-I-S-I, racing agent in food processing. Like cake, you need to raise cake. No point of making cake if you could raise it nicely. So always looking at the oven. My mom can make like very beautiful sponge cake, like so soft, yummy. Yeah. Okay, done with that. Solvay process sodium carbonate done. See, one by one. It's not hard. Okay, now we're going to make ammonia. Let's write raw materials: N2 gas, H2 gas, and we are using catalyst, iron, K2O, Al2O3, nitrogen gas, hydrogen gas, catalyst, iron, K2O, Al2O3 as catalytic promoters and everything. In modern context, manufacture of ammonia is mainly needed for the production of fertilizers. At present world, the population is nearly, I guess, 8 billion, and it had been estimated that it will be increased to about 9 billion in 2050. With the increasing in the population, production of food is a necessity. Production of fertilizer is considered as an important field of chemical manufacture. In that regard, of the total ammonia production, 83% is used as fertilizer, especially 80% of the total ammonia production is used in production of urea. The chemical reaction is this. You guys know that one. 1:3:2 plus it's exothermic. Raw material requires the production of ammonia. Now we know already. Nitrogen gas and hydrogen gas are main raw materials. Nitrogen gas is separated from fractional distillation. We already know that. Of liquefied atmospheric air. Therefore, nitrogen gas has a production cost. Hydrogen gas is obtained by cracking hydrocarbon or naphtha or using methane, which is a main component of natural gas. Okay, just need this one if you want. They are talking about this spontaneity and everything. I'm not going to do that grade part, okay? That is, the subsidiary reading. Okay, so here we're going to do different production for hydrogen. First method is the cracking of hydrocarbon. Okay. And this is the second method of production of hydrogen. This is the second method of production of hydrogen. Okay, production of hydrogen method 2. In United States, 60% of the natural gas production is used for the production of ammonia gas. Hydrogen gas can also be obtained by cracking naphtha. It also releases CO2 to the atmosphere. The relevant reaction that occurs are as follows. Okay, see, cracking naphtha, but this is again unfavorable because it's releasing CO2. And this is a third method, hydrogen production by syngas. H2O steam is passing through white hot coke. So you can make CO2, CO gas and H2 gas. So there are 3 different methods they have given to make H2 gas. H2 production, third method by syngas. H2O gas plus carbon white hot, CO gas plus H2 gas. CO gas plus H2 gas. I'm giving everything because which I could find within the syllabus. Production of ammonia from hydrogen and nitrogen gases is an exothermic reaction and it is reversible. But under normal temperature and pressure, this reaction hardly happens. The reason is the activation energy is relatively high. Production of ammonia by hydrogen and nitrogen. Industrially, ammonia is manufactured by Haber-Bosch process. The optimal industrial condition employed for the process are a temperature. Okay, optimum, not maximum or not minimum, optimal, more suitable. 450 to 500 degrees Celsius, pressure is 250 to 300 atm. Iron catalysts and K2O, Al2O3 are catalytic promoters. Remember this for inorganic as well. Okay, so this is negative. If we heat more and more, reaction is going backward. So we cannot increase the temperature to 600, 700, 800, so on. We cannot increase temperature that high. That's why we say optimum. We are not using high temperature. We are using optimum. For the exam, if you have high here, that's wrong. Okay? It's supposed to be optimum. Underline optimum. Otherwise, it's optimum. They are not doing marks. Okay, so this is a reaction. Compressibility factor, PVO-nRT. The compressed mixture of reactant gases pass over the surface of the catalyst and gets converted to ammonia. Since the reaction is reversible, the gas mixture passing the catalyst surface contain unreacted hydrogen and nitrogen gases in addition to ammonia. Therefore, ammonia gas should be separated from the mixture. When the mixture is cooled up to minus 33 degrees Celsius, because it has more hydrogen bonding, so get closer and liquefy easily comparing to these two. So by cooling this mixture, only ammonia, see other temperatures are very, very low. Liquefy and the mixture of H2 and N2 can be separated from the reaction mixture. The gaseous mixture contain hydrogen, nitrogen and ammonia under high pressure can be cooled by decreasing the pressure suddenly in another chamber. Then ammonia liquefies. Remaining hydrogen and nitrogen gases are then pumped back into the reaction chamber. Equal amount of hydrogen and nitrogen that have been used to make ammonia are then freshly added. Okay, these orange numbers are the steps. Let me explain so you can copy that down later. Okay, so we're going to introduce this first, this ammonia. Sorry, nitrogen and hydrogen. See here, my number one. Here you are introducing. Then number two is you are going through this direction. And the number three, now you have nitrogen and hydrogen pump used to insert gases to reaction chamber. This is a reaction chamber. So now you are adding here now compressed gas mixture. So this is going around here, then coming up here. Then you have the heating coil to heat, and also you are passing through the catalyst. Then heat exchanger, you are cooling down. Now the mixture is going over here. Again, to circulate gas, you are using a pump. Then you are coming over here. And then again, you have heat exchangers. Then cooling unit, you are cooling down. And now the ammonia gas is accumulating here. And the rest of the hydrogen and nitrogen are then again going for this first chamber, compressing chamber. Clear that? Okay, just if you want, you can go with these numbers, then you know the path of moving on. Hydrogen adding through this. I'll show the path like this, from here, then here, all the way 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 here. Rest of the part is moving back here. And that going around this. Here. How is this unit? Very easy. Yeah. But memory is the problem. No issue. Oh, having the memory. And almost all these reactions are from inorganic. After the, no, need one more time. After the removal of liquid ammonia, the gas mixture contains unreacted, newly added nitrogen and unreacted and newly added nitrogen and hydrogen gases under a temperature around minus 33 is heated to 450 to 500 degrees Celsius. The heat energy required to have this temperature can be supplied by the combustion of fuel also. This releases CO2 to the atmosphere. In the Hebrew process, CO2 is produced at the step in which hydrogen is produced and also during the burning of fuel to gain high temperature. Due to the overall process, CO2 gas, which is a greenhouse gas, releases to atmosphere. Globally, when 1 ton of ammonia is produced by overall process, they are talking about the environmental pollution. About 2.9 ton of CO2 is released to the atmosphere. Compared to the releasing of CO2 to atmosphere to other processes, approximately 1.4 of it is coming from this ammonia production. In ammonia production, nitrogen and hydrogen are mixed according to the stoichiometric ratio of 1:3. Since some cost has to be born to produce nitrogen gas and hydrogen gas, they are not mixed beyond their stoichiometric ratio, and this prevents wastage of raw materials. Further, in one gas, if one gas is used in excess, okay, this is your adsorption surface, okay. If you use one gas in excess, that gas absorb to the catalyst and it is cover the catalytic surface. So it does not let the other gas to come and absorb to the surface. Okay, so that is the second reason we are going with the proper ratio. Further, if one gas is used in excess, it would be absorbed by the adsorption by the surface of the catalyst, covering the surface completely. Coverage of catalyst surface by one gas reduces the chances for the reaction to occur, because other gas is avoiding from the surface. Both the gases need to be absorbed to the catalytic surface. Use of a catalyst decreases the time to reach equilibrium. Based on the factors, nitrogen and hydrogen gases are mixed in the optimal ratio 1:3. So this is negative delta S. So that if the delta is also positive, this becomes more negative. The reaction is exothermic. So it's delta S. So this is anyway delta H is negative. When the reaction proceeds, entropy decreases because the number of molecules decreases. So this is become negative and negative become positive. So you're supposed to have higher delta H. Otherwise, this is non-spontaneous. Hence, delta S of the reaction is negative. Thus, T delta is negative. So that minus T delta S become positive. Therefore, with the increase of temperature, delta G changes from negative to positive. The fact that high temperature do not favor the forward reaction can also be explained by the Le Chatelier principle. We already explained that. On increasing the temperature, the spontaneous nature of the reaction decreases. Thermodynamically, when the spontaneity decreases, the yield decreases. To increase the yield, the temperature should be decreased. But what happens when you decrease the temperature? Increase in temperature, spontaneity decreases because the forward reaction is negative. So reaction is going to backward. But if you cool down, then the activation energy problem comes. But when the temperature is decreased, the rate of reaction decreases and efficiency of the entire process is declines. A temperature optimum, that's why we are using the optimum efficiency, underline that. The ammonia yield obtained under these conditions is relatively low. Okay, anyway, if you use normal conditions, still the ammonia amount is low. Yet the production process has been designed so that the unreacted hydrogen and nitrogen gases are brought into the catalytic cycle. Even the ammonia production is lower, through this recycling through the catalytic cycle, passing this again and again, we can increase the amount of ammonia again and again. Despite the fact that the amount of ammonia yield by the single step is small, the process as a whole will gain a high yield because it has been designed to carry out by a number of catalytic cycles. According to Le Chatelier's principle, higher pressures favor the forward reaction. But maintenance cost of the plants, industrial plants, withstanding high pressures is high. It's very costly. Therefore, at present, a pressure of 250 to 300 atm is used. Maintenance of reactant concentration at a high level and product concentration at a low level results a higher yield of ammonia. This can be explained by the Le Chatelier's principle. this requirement is fulfilled by introducing nitrogen and hydrogen into the reaction chamber from time to time, and removal of ammonia by cooling the gaseous mixture containing ammonia and liquefying the gas. Removal of products, adding of reactants, move the equilibrium point forward. Okay, done with that. Uses. Uses of ammonia: production of nitric acid, fertilizers, and nylon. Number 2, petroleum industry utilizes ammonia in neutralizing the acid constituents of crude oil. Use in water and wastewater treatment such as pH control. If the effluent has or the wastewater has any acids, you can use ammonia to neutralize. Regenerate weak anion exchanger resin. Use as a refrigerant, as a cooling agent. Used in the rubber industry for stabilization of natural and synthetic latex to prevent premature coagulation. Because we have the rubber latex, by bacteria, they are adding, acidify the medium. With these acids, rubber latex gets coagulated. To avoid that, we're going to give the basic medium. We're going to talk about that later under rubber. Okay, this is the 6th one. We are done with the 5th one. We are going with the 6th one. Production of nitric acid. See, continuously we are going with same little topics. Luckily, how many more pages, Dhoni? Really? Okay. Let's write raw materials. Ammonia, air, water, platinum, rhodium, catalyst. Raw materials. Okay. Ammonia, air, water, platinum, rhodium, catalyst. For this, ammonia gas, atmospheric air, and water are used as raw material. Nitrogen dioxide gas obtained by the reaction between ammonia and oxygen gas is reacted with water to produce a nitric acid. So these are the reactions then. Ammonia, because we are directly using air. So this stoichiometric ratio is 4:5. But here you are using 1:9 because we need to provide more air to give exact amount of O2. All these processes are exothermic. Step 1, step 2, step 3 mean oxidizing ammonia, we are producing NO. And that NO again oxidizing with oxygen, we are getting NO2. And that NO2 with directly with water, we can produce nitric and NO. But that NO again oxidizes O2 to produce NO2. So all those NO2 together with water oxidizing again with O2, we are producing nitric acid. Adding ammonia here. So we have this ammonia NH02 here. And we have this catalyst here. So NO gets here. Then again, we are adding O2 in this oxidizing chamber, O2 NO2. Then we are adding that NO2, again concurrent from here to here. And then water from here to here. So it's making nitric acid. So this arrow is supposed to go the other way, okay? So we are making nitric acid. Make the arrow going out, water out, or the nitric out. In the first chamber, ammonia is oxidized in the presence of catalyst. In the second chamber, nitrogen monoxide gas, nitric acid, is oxidized. Nitrogen dioxide gas is reacted with water in the third chamber. Ammonia is oxidized using atmospheric air, from which dust and water vapor have been removed. Ordinary air contains 78% nitrogen and 21% oxygen by volume. Volume of atmospheric air, which contain the required amount of oxygen. Is pumped into the reaction chamber. For a unit volume of ammonia, 9 to 12 unit of atmospheric air must be required. A high temperature range, 800 to 850, is maintained. Under these conditions, 97% of NO gas can be obtained. If the ammonia concentration is high, explosions may occur. Therefore, maintaining the volume of ammonia and atmospheric air is in the correct proportion is important. When the gas mixture is passed through the platinum rhodium catalyst under pressure, it is converted to NO gas. This NO gas is cooled to 150 degrees Celsius. When the temperature is 150, further oxidation of NO to NO2 occurs in the oxidizing chamber. In the adsorption chamber, NO2 gas is allowed to react with water, conforming to the countercurrent principle. The gas mixture contain oxygen. NO2 gas is pumped into the absorption chamber under a pressure of 5:10 atm. As the absorption chamber is packed with chemically inactive substances, greater chance is offered for the reaction between water and NO2 with that countercurrent principle. Initially, the yield is 98%. That's done. Uses of nitric fertilizer, essential industries like potassium nitrate, gunpowder, silver nitrate, photography, aqua regia. If you have forgotten, we did inorganic analytical part, HCl nitric 1:3:1. Cleaning surfaces, welding, manufacturing of superphosphate. Let's try that. Manufacturing, number 5, manufacturing of superphosphate. Okay, done with nitric. We are moving to our 8th production. Number 7. Seventh one, sulfuric acid. That's again familiar. We done this for inorganic as well. Sulfur, A, and water. Sulfur, A, water. Raw materials required to produce sulfuric acid. Sulfur or ores containing sulfur and water are used in the manufacture. When extracting the metal, lead, copper, and zinc from ores containing lead sulfide, copper sulfide, and zinc sulfide, sulfur dioxide is obtained as a byproduct. This can also be used to produce sulfuric. Sulfur obtained by byproducts during petroleum refinery or sulfur extracted from earth can also be used. In the production of sulfuric acid, sulfur dioxide is made by burning sulfur or metal sulfides. Second step is the preparation of sulfur trioxide by reacting sulfur dioxide with atmospheric oxygen. Sulfuric acid is obtained by hydrolyzing pyrosulfuric acid, that is oleum. We know that pyrosulfuric H2S2O7 oleum, made by the reacting sulfur trioxide with concentrated sulfuric acid. Today we're going to learn everything why we do such. Sulfur oxygen SO2, and this is the reversible. Here we are using this vanadium pentoxide catalyst. We are not increasing the pressure because with this condition we're going to get this very pure 98% sulfuric. So temperature is given, making SO3. That SO3 absorbed to sulfuric to get oleum. Very nice, very slowly reacting volume with water, we can get sulfuric. Production of sulfur dioxide by burning elemental sulfur is a separate process. In the school laboratory, sulfur dioxide can easily be prepared by burning a piece of sulfur with a Bunsen burner. But production of sulfur dioxide industrially is not that easy. First, sulfur is heated to 140 degrees Celsius and melted. Liquid sulfur is filtered to remove various solid impurities in it. Okay, whatever the way, we get the liquid sulfur and dry air to burn that. So with air, you're going to get O2. So you are making that SO2 here, going through this catalyst. Then you have SO3 here, making SO3 here, okay? that SO3, again concurrent, from here to here concentrated acid, downwards to upward, SO3. So water vapor removes from the top, oleum comes down very slowly, then oleum is reacting with water to get sulfuric. This is the furnace and this is the converter. Okay. See, I told you this is easy, but don't take this easy. What happens is you are taking this too easy. Then later when you are doing questions, you only identify that you don't have a memory. Read it. I'm only asking you guys to read this. Okay, solid sulfur. Heating, you're going to get liquid sulfur. To neutralization, you're adding calcium oxide. Liquid sulfur with solid impurities, you filter that. You get the liquid sulfur. This is the purification process. Pump to the burner. Then this is you are getting SO2, reacting with O2. Liquid sulfur and atmospheric air should be pumped into the furnace. Liquid sulfur is pumped in the form of very small droplets with the to burn easily. Combustion of sulfur is exothermic. In the gaseous mixture obtained after burning, the composition of sulfur dioxide is maintained to 8 to 9. That again, let's discuss. Okay? They have this another picture. The temperature around the burner is 830. In the gaseous mixture of sulfur dioxide, oxygen, and because don't forget we are using atmospheric O2, so it has nitrogen as well. Now all are going to combustion chamber. Various solid particles and ashes may be present. Removal of them is crucial because the particles of dust and ash setting on the surface of these vanadium pentoxide catalysts retard the catalytic action. Therefore, first the gaseous mixture containing SO2 is purified. The reaction producing sulfur trioxide is reversible and exothermic. The molar ratio by the volume between oxygen and sulfur supposed to be 1 to 1. Here, because sulfur dioxide is 1 to 1, because here we can get oxygen like easily. It's cheaper. So we're going to use more oxygen. It's supposed to be 2 to 1, but here we are using 2. Understood? It's supposed to be 2 to 1, but here we are using 2. So more oxygen. For efficient progression of the reaction, an optimum temperature 400 to 500 is maintained. The reaction itself generates heat. Thus, if the production plan was designed to react the whole amount of SO2 with O2 at once, a huge amount of heat would be liberated. This favors the backward reaction and reduces the yield. Hence, the entire amount of SO2 is converted to SO3 in 4 steps. In every step, the gaseous mixture is passed through the catalyst bed. In order to increase SO3 yield by shifting the above reversible reaction to the right, oxygen concentration can be increased by supplying atmospheric air. As atmospheric air is a cheap raw material, this does not increase the production cost. According to the stoichiometric ratio, it's supposed to be 2:1, but we are giving 2:2 or 1:1. The amount of oxygen required for 1 mole of SO2 is 0.5. This is 1, this is become 0.5. 2:1 mean 1 to 0.5. But during the production of mole ratio maintained as 1:1, so that's 0.5 mole of O2 in the excess of 1 mole of SO2. Though atmospheric air is cheap, maintaining a higher oxygen concentration about the required concentration decreases efficiency. So only going with the 1:1, otherwise it decreases the efficiency. This is because the higher oxygen concentration, more O2 molecules get adsorbed. The same reason for nitric. If more O2 adsorbed onto the catalytic surface, its performance decreases. This reduces the capacity of the catalyst to adsorb SO2 molecules thereby decreasing the probability of the reaction to occur. This reaction is exothermic. Therefore, increase in the yield of cooling can be predicted from Le Chatelier exothermic going forward. If you heat, reaction go backward. But the decrease in the rate of a reaction at low temperature brings down the efficiency, same as the earlier. You need temperature, but decreasing the activation energy. Okay? Efficiency of the production process. Hence, it has been decided that the optimum temperature, again underline, optimum temperature is 400 to 500. Le Chatelier principle predicts that the increasing pressure, the reversible reaction tends to move in favor the direction in which the number of molecules in the gas phase decreases. In this reaction, increase the pressure favors the forward reaction, but again, same as the earlier one, we are not doing that. Increase in the productivity is SO2 is okay, but in the particular reaction, the yield already we are getting 99%. So why we are using higher pressures with higher prices? Therefore, applying high pressure is unnecessary. Okay, we are going with set of reactions. So nitrogen is, because it's atmospheric air, you have just nitrogen is there. So the first catalytic chamber, temperature is 17, SO2 is 70%. So the next temperature, SO2 is 90%. Next temperature 447, now the SO2 is 98%. So always like the same reaction, SO2 plus O2, SO3. Little by little, first chamber, second chamber, third chamber, finally you are here. So then we are cooling, and remaining SO2, SO3 are again recycling here. But then this intermediate H2SO4, it's possible. But we are basically making oleum reacting with water, reacting with SO2. This SO2. And then with that, we are making final H2SO4 adding with water. Okay. The temperature of the gas entering, anything you want to write, Tony? Yeah, 70. Is that a printing error? Yeah, 70. The temperature of the first chamber is around 670. When passing through the catalyst, the temperature rises to 890, and about 70% of SO2 get oxidized. Then gas cooled about 700 Kelvin, 427, is passed through the second bed of catalyst. At this stage, amount of SO2 present is relatively low. For this reason, the amount of SO3 forms is less than that formed in the first step, and the amount of heat generating is also relatively low. The second heat exchanger cools the gaseous mixture, whose temperature has risen to 770 from 770 to 720. By that time, a considerable amount of SO2 from its initial amount has reacted. After passing through catalyst or the catalytic bed in the third chamber, 98% of SO2 is converting to SO3. Sulfuric acid is made by SO3 obtained from the third step. Here also 100% of SO3 is not converted to H2SO4. The gaseous mixture contains the remaining SO3, and the SO2 left due to the reversibility is heated again and passing through the catalyst in the further fourth chamber, which convert it to SO3. This SO3 is also converted to H2SO4 again. The reaction between SO3 and water is violent and highly exothermic. Therefore, water vaporizes. This is the reason you cannot do that. Vaporizes, and mist of sulfuric acid fume is made. It is not making liquid, it is making the mist. To avoid this, SO3 gas is converted to H2SO4 via the steps described above. Oleum, then plus water. The absorbed SO3 is maximum in concentration, 98% sulfuric acid at 70 degrees Celsius. Therefore, under this condition, SO3 is absorbed into the concentrated sulfuric acid and H2SO4 is made by adding water to it. Sulfur trioxide and concentrated sulfuric acid are reacted according to the counter-current principle. This happens in the absorption towers, which are packed with ceramic material. Because of the packing, sulfuric acid slowly trickles down the chamber from top to bottom and the surface area of the liquid H2SO4 is increased. Sulfur trioxide moves up the chamber. Counter-current principle. Increasing surface area of the acid coupled with its slow flow and upward movement of SO3 gas makes the absorption efficient. Here SO3 gas reacts with H2SO4 to give the oleum. Concentrated sulfuric acid is made by adding water to oleum. Carefully. Done. Uses of sulfuric. Production of phosphate fertilizer, ammonium sulfate fertilizer, artificial fibers, including rayon and plastics, production of detergents containing alkyl and aryl sulfonate, production of dyes, explosives, and medicines, production of battery acids. Battery acid is sulfuric. Drying gases like Cl2,8 to clean the surface of iron before galvanizing. To clean the surface of iron before galvanizing. Number 9, uranium extraction. Number 10, to extract titanium from ilmenite. To extract titanium from ilmenite. Okay, done. Number 8, to extract titanium from ilmenite. Okay, so now extract titanium from ilmenite. Oh, rutile. Rutile is definitely TiO2, but this is my darling. Rutile is exactly the TiO2. We are finally making TiO2, but the difference is this TiO2 is an O, so it has a lot of impurities. So we are making pure TiO2, either from rutile or ilmenite. So these are the raw materials of production of titanium dioxide and rutile. Ilmenite and rutile are main minerals which contain titanium. The minerals in which titanium is present in abundance in the form of TiO2 is rutile. Ilmenite is a mixture of the two oxides TiO2, FeO. Sometimes that also say Fe, TiO3, right here, Fe, TiO3. When producing TiO2 using ilmenite, first FeO in it is removed. This increases its TiO2 percentage. Removal of FeO from ilmenite is called sulfate process. High purity TiO2 is produced from ilmenite, in which the percentage of TiO2 is brought about 70% by removing FeO. High purity TiO2 can be produced starting from ilmenite purified until its TiO2 percentage is about 70% or by using rutile. The production process is referred to as the chloride process. So the sulfate process is to removal of iron. So the chloride process is converting TiO2 to titanium. Chemistry of the production of titanium dioxide from rutile, chloride process. The aim of the process is to remove various inorganic impurities in rutile and produce high pure TiO2. It comprises two steps: chlorination, oxidation. Chlorination means this untidy titanium oxide solid has all the other impurities. So first we reduce it to solid, but still this has carbon and titanium and other gaseous, other solid impurities. Then we react all these mixture with chlorine. Only titanium is reacting with chlorine, and most importantly, it is making the gas. So we can separate TiCl for gas, but that's a gas. So that is the chlorination. Then TiCl4 oxidized to get TiO2. Drying to remove moisture in rutile and coke is indispensable. For this, they are dried well by heating to 200 to 300 degrees Celsius. For chlorination, the mixture of rutile and coke or carbon is heated to about 950 degrees Celsius, and steam of chlorine is passed over it. In the presence of coke, titanium dioxide reacts with chlorine, giving titanium tetrachloride gas as the product. This reaction is exothermic. The main reason for this is the oxidation of coke giving carbon dioxide. The relevant reaction are, because of making carbon dioxide, this is exothermic. Total reaction we can show like this. The boiling point of titanium tetrachloride is 134, but here we are giving 950. Therefore, at 950, it is containing gaseous and carbon dioxide. In addition, dust particles and as a result, a side reaction, hydrogen chloride and carbon monoxide gases may also occur. HCl, carbon monoxide are possible because you have hydrogen, chlorine, but here inorganic impurities present in TiO2 are removed. After the removal of dust particles, liquid TiCl4 is separated by cooling the gaseous mixture. After further purification of separated liquid TiCl4, it is oxidizing. Okay, see the oxidation mean reacting with O2 to give TiO2. And this is making Cl2, so going back to recycling. Here TiCl4 produced in the first step is reacted with oxygen and TiO2 is generated. This process is important for production of pure TiO2 free of inorganic impurities present in rutile. Resulting chlorine gas is used again for chlorination, that's a recycling. Therefore, chlorine gas is recycled. During this process, coke is oxidized, coke means carbon, oxidized, and carbon dioxide is added to the atmosphere. Now we are talking about the environmental pollution. Hence, chloride process contributes to global warming. In 2006, CO2 released to atmosphere by this industry is 3.6 million metric tons. Half of this was due to the burning of fuel and raised the temperature, and the other half was produced by the production process itself. Okay, done that, users. TiO2 is white in color, therefore it is used as a pigment to obtain bright white color in paints, plastic goods, and paper. High refractive index so that they are opaque. Opaque means light is passing but we cannot see through. Not if. Of Ti2 is also a reason for using it as a pigment. TiO2 is chemically inert, therefore it is used as a pigment to give white color for the medicines and toothpaste. TiO2 is also used to produce substances applied to prevent sunburns in the skin due to UV radiation in solar rays. TiO2 prevents the reach UV radiation to the skin. You guys have to maintain least some sort of a sunscreen least on your face. Okay. Otherwise, when you go like in your 40s, you're going to get these like, you know, the black patches, dark color patches on your skin. Cancers. Now the sunlight is like more stronger. Okay, it is used to make some solar cells. Okay, done with that. So the ninth one. How many pages are together? 95. We need to finish these 50, let's see. Okay, extraction of oil. So these are the raw materials, iron ore, plus coke, plus limestone, plus A. Right. Iron ore, coke, limestone, and A. Read me any question? Okay. Little not important, but I am going to read it. We have an ancient history of production of iron. Archaeological Puravidyatmaka studies have revealed that the ancestors of this country, Sri Lanka, were aware of iron extraction thousands of years ago. They have extracted iron using natural wind power and wood charcoal. Jill Juleff, an archaeologist of the University of Exeter, England, has confirmed the technology of iron extraction prevailed in this country by recreating an old iron extraction furnace at the Wind Gap, Hulankapolla at Balangoda. Really, Hulankapolla? They have this furnace over there, like ancient furnace. Really? I'm going to go there to visit those. Have you guys seen? Okay, her findings have been published. You don't want that. Raw materials essential for iron extraction, iron ore, limestone, coke, or coal, or A. The furnace used to extract iron using the above raw material is called the blast furnace. Inside of the blast furnace is lined by the special type of bricks withstanding higher temperature. The mixture of the iron ore, limestone, and coke is fed into the blast furnace, form the inlet at the top, while A is introduced near the bottom. Molten iron is tapped out. This is a tapping out. From the bottom end of the furnace, the slag, I'll explain everything, is removed the bottom part other than the iron. Rest of everything other than the iron is called the slag, is removed a little above the level at which the molten iron is tapped off. In the blast furnace, a mass flow occurs from the top to the bottom under gravity, whatever the mass, solid stuff. Simultaneously, compressed air is going from, again concurrent, air passes from the bottom to the top. Since substances flow in opposite direction from the bottom to the top and from the top to the bottom, possibility of the reaction is occur between the solid phase and the gas phase increases. This also creates a temperature gradient. Moving on. Okay. Whatever these iron ore, limestone, or coke, introducing from here, and hot compressed air, burning fuel and everything we are passing here. So from here to here, temperature is decreasing. Highest temperature and lower temperature. Then air has also O2 as well. And so the reaction occurs when it is coming down from here to here. Then it is making this iron, and rest of everything is existing here as a slag. And slag is less denser than molten iron. So the molten iron stays down here. This is the molten iron part. So that avoids the oxidation of this extracted iron from this atmospheric O2. Clear? That's again the second benefit. Since both these are liquid, so we can pump out this here, and also we can pump out iron from here. How much temperature can you imagine? Melting iron through a tap getting out? Some facts to which attempts should be drawn in the process of iron production are given below. Ratio among the components of the mixture of ore, coke and limestone, particle size, rate at which the mixture is added to the blast furnace. From the top, blast furnace is that oven. Rate of flow of air, current, and its pressure. Here, the role of coke is as follows. Coke is really important. Fuel plus main reducing agent. Fuel plus main reducing agent. Number one, as a fuel. So, exothermic minus 395 per mole, kilojoule. Acts as a direct reducing agent. It directly reducing, and also it is also producing carbon monoxide. Carbon monoxide is the main reducing agent of iron here. Okay. It is written here. It's written here on the note. A deposition of silicate. Okay. Okay, because we are using this calcium carbonate, and iron also has these silicates and aluminates. That's why we need limestone, calcium carbonate, converts to calcium oxide. That reacts with silicates and aluminates to make calcium silicate and calcium aluminate. So all the silicates and aluminates coming from ore is now separated. These two are called the slag here. See, these two are the slag here. Okay, going out from here. Deposition of silicates and aluminates in the ore should be prevented as impurities in iron. Calcium oxide obtained from the thermal decomposition of calcium carbonate is useful in this regard. Calcium silicate, CaSiO3, and calcium aluminate, this form are called the slag. The density of the slag is lower than the molten iron, therefore liquid slag layer floats on molten iron. As the slag covers the surface of molten iron, the chances of molten iron to react with oxygen is less. From the lower part of the blast furnace, hot compressed air is injected into the furnace. Coke burns, and with admission of air, burning reaction is speeding up. The rate of the burning reaction is decided by the temperature of the hot air, pressure, and the size of the coke particles. As the combustion reaction is fast and the combustion of coke is highly exothermic, large amount of heat is evolved in a short period of time. Therefore, the temperature of the basal part of the furnace rises at once to about 1700. The rate of the combustion reaction and the amount of coke burned are important factors in maintaining the temperature of the basal part stable. It is important to maintain the rate of airflow upwards and the rate of mixture containing coke flow down to maintain at optimum. It makes optimum, it makes increase the reaction rate. Hot carbon dioxide gas formed during combustion passes upwards through the air, upwards through the hot carbon dioxide gas, through O. Through O comes down, carbon dioxide goes up. At high temperature, carbon dioxide reacts reversibly with coke, forming carbon monoxide. Okay. High temperature is in the bottom part. At the bottom part, if you have coke with carbon dioxide, it is making carbon monoxide. Number of gaseous molecules increases, therefore entropy increases. Entropy increases mean it is more spontaneous. Entropy is positive for this reaction. When the temperature increases, magnitude of numerical value of T delta is also increasing. At high temperature, in the presence of coke, there is a tendency for reduction of carbon dioxide to carbon monoxide. Clear? That happens only at high temperature, so at the bottom, because the temperature high means more spontaneous. Under such conditions, carbon monoxide gas is relatively stable thermodynamically, because this is forward direction is spontaneous, so this is more stable. So that's the bottom part of the furnace. When the temperature is around 1000, nearly 100% of CO2 is converted to CO. Okay, down there, 100% of CO2 is converted into CO. Okay, so when the temperature increases from up to 100 degrees Celsius, it has the highest, or the 100% carbon monoxide. The temperature is 1000. That has 100% carbon monoxide. Clear? O2 plus carbon dioxide plus heat. Number of gaseous molecules does not change. So for this reaction, entropy doesn't make any issue. Reaction is exothermic. Here you have only one, here you have only one. No change of entropy when reacting with carbon with O2 to make CO2. This second one, when it is making carbon monoxide of O2 plus carbon CO, here 1 is to 2. So entropy increasing exothermic. So this reaction is more favorable than making CO. Because both reactions are exothermic, delta H is negative. When the temperature increases, reaction 2 has the conspicuous or obvious or considerable increase in value of T delta S. With temperature is marked increase in the negative nature of delta G is expected for reaction 2. This one become more negative when temperature is high. When the temperature drops, thermodynamically stability of, okay, so that when the temperature is decreasing, CO stability, so that is decreasing, because here is going back to make, not the making back, but it is decreasing the amount. Clear? When the temperature drops thermodynamically, the thermodynamic stability of carbon monoxide decreases, thermodynamic stability of CO2 increases, because making CO2 is better in low temperatures. Because the forward reaction here is not that favors at high temperature. Understood? Because here entropy doesn't make anything, but when you increase the temperature, reaction is going backward. So the low temperatures are favorable to make CO2. Higher temperatures are favorable to make CO. Okay. Half an hour. I'm trying to finish today. So next day we can finish this lesson. Since the temperature of the bottom area is as high as 1700, CO gas is formed liberating heat when CO2 gas interacts with red hot coke in the mixture. When CO gas formed in the hot lower region of the furnace moves up through the mixture containing the ore, the stability of CO decreases because the temperature decreasing. Hence, the tendency of CO becoming CO2 now increasing. As oxygen gas is not available in the region above, at where the coke is burnt in the furnace, CO oxidizes to CO2 by reducing Fe2O3. Going up, it has to reduce. So it has to oxidize. CO supposed to oxidize to CO2. But for that, you don't have oxygen. So it needs some sort of a source. What is the source? Source is the iron ore. Now it is starting to reduce Fe2O3 to iron. Understood? But this way first, okay? Let's read. As a result of this, Fe2O3 is gradually reduced. Going upward the furnace along with the decreasing temperature, so reduction of Fe2O3 in the ore continues. At temperatures below 1000, reduction of Fe2O3 can be indicated. Okay, below 1000, so reduction goes this way. Fe3O4 ferroso ferric oxide is still having part which is not reducing. Clear? part is existing as +3, not reducing, but part is reducing from +3 to +2. It's a mixture of FeO and Fe2O3. About 33% of the iron in +3 oxidation state in Fe2O3 has reduced to +2. Only part is reducing. Carbon monoxide, FeO, part is CO2. Or otherwise, we can just directly write Fe3O2 plus CO, FeO plus CO2. That FeO with carbon monoxide going up become iron and CO2. Clear? See how nicely explaining. Fe2O3 partially reduces to Fe3O4 and this mixture goes down the furnace. There, it further reacts with carbon monoxide gas and its iron atom of +3 state reduces to +2 oxidation state, FeO, which is formed as a result, reacts further with carbon monoxide gas and reduces up to free iron. Further decomposition of calcium carbonate occurs at a temperature below 1000 degrees Celsius. Carbon dioxide gas generated by it also has the ability to react with coke to produce carbon monoxide. Even this produces carbon monoxide when going upward the furnace by reacting with Fe2O3 in the ore, possible to become CO2. Going up, unstable, CO becomes CO2. About 1000, that in somewhat in a lower part of the blast furnace, following reactions are possible. In this region, coke directly reduces iron oxide. Okay, FeO with carbon directly can go to iron and carbon dioxide. And also CO2 plus carbon gives CO. That CO going up, making this, reacting with this, making this iron. And also there is this possibility carbon monoxide, if in case there are oxygen to react, it is making CO2. In the blast furnace, a part of the total amount of coke participate for the combustion reaction. Another part with CO2, another part react with CO2 to produce CO. Another part reduces FeO. A acting as an oxidant and generates heat and CO2 by the combustion reaction. If excess air is supplied, thermodynamically it is likely that the addition of reaction with Fe2O3, we cannot add more A because it oxidizes back this reducing reaction. Carbon monoxide would react with oxygen to give the carbon dioxide. So we cannot use more oxygen. This is disadvantageous. Therefore, in the extraction of iron, it is very important to maintain the volume flow rate of air and the flow rate of solid mixture containing the ore at an optimum level. In the lower part of the furnace, the amount of O2 decreases at once, but producing a proportionate amount of CO2. For this reason, there is a sudden increasement in the concentration of CO2 and production of intense heat. This CO2 in the high temperature zone tends to move up through the solid mixture, falling down. Clear? Don't get sleepy here because you guys are not doing only listening, okay? Are you guys okay? Therefore, the reaction of CO2 with the coke in the solid mixture occurs in the lower part of the furnace where the temperature is high. Because of this, when the CO2 concentration gradually decreases, CO concentration increases. Even CO generates in the lower region passes upward through the solid mixture. Continuously, same thing, repeating. Ascending the furnace, the temperature decreases. So the thermodynamic ability of CO gas decreases, thermodynamic stability of CO gas decreases, while the tendency for conversion to CO2 increases. As O2 is absent, CO gas gets oxidized to CO2 gas by abstracting oxygen from Fe2O3. So that going upward the furnace, carbon monoxide concentration decreases and CO2 concentration increases again. I don't think this much very, very finely, repetitively, not necessary to explain, but that is the lecturer who has done that. I know that the person, he is different, I guess. Because of the use of coke, CO2 is released from the furnace and this causes global warming. Thus, seeking renewable alternatives for is environmentally important. Avoiding unnecessary use of carbon is also, iron is also important. It's non-renewable coke. Done with that. 11th one, polymers. Sorry, 10th one. 10. Number 10 here. Polymers are formed by a chemical bonding of a very large number of relatively small molecules referred to as monomers. Monomers together make polymer. We can go with a couple of examples. Ethylene. This one breaks to this side and this side. Let's say another CH2 breaks from this side and this side so that these two can join together. No more double bonds. Okay, this is one ethylene and this is another ethylene, the double bond. No more double bonds here. So what kind of bond breaking is there? Mechanism supposed to go with what? Elimination, addition, substitution, redox. Elimination. Understood? Sorry, addition, breaking bonds. In an organic. Okay? This is again addition, double bond breaks, and you just wanna make this printing error. Just write the page number. Remove that chlorine, it has to go to the alternative. Okay, styrene mean same. See, you can easily remember. This is the ethylene. Vinyl chloride, one hydrogen gets away, chlorine joins. Styrene, one hydrogen gets away, benzene joins. Polystyrene, polyvinyl chloride. And here, all four hydrogens have gotten away. Tetrafluoroethylene or Teflon. This is called Teflon. Tetrafluoroethylene. TTFE. Due to the joining of a large number of monomers like this, the carbon skeleton of the monomer is repeatedly placed in the monomer. Therefore, it is called as repeating unit. Okay, so that even we can draw like that. We can again show the repeating unit. Only this one. But when you are repeating, you cannot show the double bond because in the final, this one, you don't have double bond here. This is the polymer and this is the repeating unit of that polymer. You don't have double bond, but this is the monomer. 3 different structures. Understood? 3 different structures. The repeating unit of polyethylene is CH2CH2. As there is a large number of repeating units in a polymer molecule, the molecule is symbolized by writing n number of, like large number of molecules are here. N number of molecules are here. I have back pain today because I'm always slant into this tab. Okay. But I'm going to do this to finish this next week. Then being very relaxing, we're going to start organic. How come you guys not requesting the organic revision? Remind me. Did I send you? No. It is something very simple, just going through the note. I don't want to do it like wasting my time. Okay, so this is the ethylene. And this is the polythene. And we are using it for trash bags, packing materials, seat covers, bottles, various containers and toys. And vinyl chloride, this is a polyvinyl chloride, does not catch fire easily. And water pipes, I'll enlarge so you can write. Let's listen. Wire insulators, films, floor seat covers. So styrene, so polystyrene is one of the polystyrene is rigiform. Now you know what is a polystyrene. Insulating materials and packing materials. So this is a tetrafluoroethylene Teflon. That's again withstand high temperature. So fireproof, non-stick Teflon seals gaskets in plants using in chemical industries. Okay. Okay. Production of polymers from monomers is called polymerization. According to the reaction occurs in polymerization, polymers can be classified into two classes. See, we know this. Addition mean when you're having a double bond, breaking or double bond is addition. Condensation mean actually elimination. Condensation mean you make two molecules together by eliminating smaller molecules. So that is the elimination. You can write that. Addition is the double bond. Condensation mean elimination of small molecules. You can have the better memory understanding. Okay, if a polymer is formed by a bonding of monomer by the addition reaction, such as polymer is known as addition polymer. The unsaturated bonds in the monomer are important in this regard. The molar mass of the monomer is equal to the molar mass of the repeating unit of the polymer. However, the three-dimensional structure and the hybridization state of the carbon atom of the monomer and the repeating units changing. Okay, see, depending on the hybridization and everything. So you're gonna remove this bond, double bond. So let's say, one molecule, the second molecule, oops, second molecule, and then the third molecule. Clear? Okay, during the formation of condensation polymerization, condensation reaction occurs. Therefore, in addition to the polymer, small molecule of low mass are produced. For example, ester bond is making between COOH and OH. This OH and this H gets away to make water molecule. Hence, the production of polyester, a condensation reaction takes place. A number of water molecules equal to the number of ester bond making. Yeah, that's you guys. That. Show this water molecule here. Show this water molecule. This OH and this H, okay? Release. If the volume of water produced to be measured correctly, the number of ester bonds formed could be calculated using the density of and monomass of the water. Because if we know the number of water molecules released, from that we can find how many ester molecules been used. And here, so that this part is this part here, and this part is now this part. Understood? So that is only the monomer part then. That is a repeating unit. So n numbers together showing this polymer here. In terms of the repeating unit, the structure of polyethylene terephthalate PET can be shown as above. Polyamides are okay. Amides. See, if you go with the amide, you guys know that amides are making between ammonia and carboxylic acid. So one of these hydrogen gets away with this OH, water molecule gets away. Okay, so this part is this, and this part CO, that part is this part here. And this part has six carbon, and this part has 6, 4, 5, 6. So this carbon in dicarboxylic, and this is not nitrogen, this is carbon. Printing error. Number of carbon atoms in diamine. You can write the page number. So that monomer we can show like this. Okay, so single chain is called the linear polymer. This is a single chain linear polymer, and also they can go like this. See, this is three-dimensional, 3D. Like there are more active sites that this can join, like 1, 2, and 3. So you are joining with this carbon. Like if I show this this benzene, or this benzene and this oxygen, benzene, this part. So 3 active sites. All these 3 active sites can join with this part. Okay. So these 2 hydrogens get away with this oxygen. So only the remaining part is this carbon here. Only this carbon is remaining. Understood? All the circles are water molecules are getting away. Clear that? So these are the 3D polymers. So that only this formaldehyde, this is a phenol, this is a phenol, and this is a formaldehyde. Phenol part is there. From the formaldehyde, only this CH2 is remaining. So you can go with like whatever the direction. So these are 3-dimensional polymers. Sometimes the polymers are formed as 3-dimensional network. The reason for this is that the monomer has more than 2 reactive sites. If we consider phenol as an example, the number of sites in the benzene nucleus at which substitution can take place is 3. A 3-dimensional network polymer is formed by the reaction between phenol and formaldehyde. And that compound is called the bakelite. The polymer is known as bakelite. Bakelite is really, really tough, and you cannot You cannot wash it again with chemicals to get this glassware. So at university, as I remember, we were using something disposable to make bakelite because you cannot clean it back once you make bakelite. In such instances, a specific repeating unit cannot be identified. Okay, if it is a three-dimensional, there is no repeating unit. We cannot show any repeating unit. According to the nature of the structure, polymers can also be classified as linear, branch, or network. Bulletproof glass or glass? Maybe part of polymer. I have no idea. I never checked that. What is the question? I would try. I would try today. If I find something interested, I'll write it. Okay, PS polystyrene, PVC polyvinyl chloride, PTFE Teflon, PET polyethylene terephthalic acid. We have all these names. Polymer molecules have a linear structure. These are linear. Linear means there are no cross linkages. So you can make branch this way or continuously going the branching make the network. Linear and branch polymers are packed in various ways as separate molecules. Sometimes in some region, okay. So if you go with the linear, various ways they can pack, okay. Some regions, the molecules are closely packed and orderly arranged. Such regions are called crystalline areas. Some are twisting and entwined, winding and twisting with each other, with one another. Such regions are called amorphous regions. Some polymeric substances are totally amorphous, but some polymers have contained amount of crystalline and amorphous both. Such substances are known as semicrystalline polymers. Polythene, okay, have you guys seen this? Sometimes when you see through these polythene papers, there are like thicker part and thinner parts. So the crystalline and amorphous parts together. But some polymers have the certain amount of crystalline region. Such substances are known as semicrystalline polymers. Polythene is an example for semicrystalline polymer. Light does not penetrate well through the membrane of semicrystalline polymers. Crystalline polymers of them settle, crystalline region of them scatter light and reduce transparency. Light does not scatter through semicrystalline layers, therefore they are transparent. Amorphous region have this entwined nature. Polythene can be synthesized so that a branch structure is obtained. Linear polythene molecules pack closely with each other and have more high density areas. Such polyethylene are named as high density polythene HDPE. When branched, the molecules do not pack that closely. Their density is low and have more amorphous region. This type of polythene is referred to as low density polythene, LDPE, low density polyethylene. Okay, rubber and plastic. Rubber is considered as, I guess it's a long topic if we go to the next one maybe. Yeah, rubber is a couple of pages long, the topic. Yeah, very long. Rubber, let's do the next day. Let's start from there. Okay. Dhoni, how do you feel? This industrial and environmental. Easy. Going. Dhoni? It's okay. It's easy. I know it's easy, right? Just after reading, you can understand nicely. But the only thing is the memory, okay? So you have to live with this book. Next week, once we finish that, keep the book very close by you always. So just read, not memorize, just read. And you have the issue like how it is, how they are floating. Huh? It is not floating. This is the, no, yeah, this is the stick which is joining to an arm here. To that arm, there is a seat. Then they are wearing this, they sit. Yesterday, the Sinhala medium like, like they are wearing something inside. So this cloak they wear after they sit. By that cloak, they cover the chair and everything. Understood? So the chair is fixed here. And their hand and the arm is here. With their arm, the chair arm is also here. It's wrapped with this cloth. So that's why you don't see that. So she was beautiful. So just otherwise you can look at a girl. But she's like displaying. So I think ළඟට ගිහිලා බල බල වටේ ගිහිලා ගිහිලා සර්ච් බලනවා. අත්තනේ වෙලා තියෙන්නේ මේ පොල්ලට හයි කරලා තියෙන්නේ. That's the reality actually. Huh? No, I guess that's a steel or something, I guess. Yeah. Sometimes they do transparent here. This one too. You know, the polyacrylic and those are really tough. Okay, even the bakelite are tougher, you guys know now. Okay, then let's stop there. Next week, we can definitely finish this one. So after that week, we can start from organic. I want you guys to go with organic short note and spider diagram. Go with each day for now, for these 2 weeks, read organic short note. 1 week you can read the organic short note, then only start the organic tutorial. Organic tutorial become really, really easy if you go with the, not the spider diagram, organic short note that I have given. Okay, bye, take care then.